Now I would like to officially welcome you to MaX School Materials and Molecular Modeling with Quantum Espresso. This course is organized by MaX, COE, and a couple of national competence centers, the National Competence Center of Austria, Czechia, Hungary, Poland, Slovakia, and Slovenia, with the support of IT for Innovation's National Supercomputing Centre, which provides the infrastructure. This course is organized in collaboration, as I said, and it is dedicated to a quantum espresso code. The emphasis will be on practical skill development. The course strikes a balance between theory and application, offering a hands-on learning experience. It caters to a beginner to intermediate level, aims to equip participants with the fundamental knowledge and skills necessary for the effective utilization of the quantum espresso code in their research and academic pursuits. We have a big group of tutors from the MaX COE: Paolo Giannozzi, Stefano de Gironcoli, Pietro Delugas, Oscar Baseggio, Anton Kokalj, Matic Poberžnik, Laura Bellentani. They are from different institutions, so you can see it on the slide. And with this, I will pass the speech directly to the first tutors.
Yeah, I'm Oscar Baseggio. Thank you, Karina and Lucy, for the organization of this school. Do you see my screen? Yes. Okay. This is the virtual machine. If you open the browser, the Firefox browser, the home page is the HackMD page. This is the HackMD page. Maybe I copy the link on the chat, so you can find also in the chat. Where is the chat of Zoom? So here. You can find here to make the question. You can find here in this link for day 1, question and answer. Click here, open this page, and if you write here some question, maybe minus space, you can find here appear the point, and maybe can ask what's your name. And if you go down and press tab, you can name is, so everybody can see the question and the answer, and this file remain for also in the end of the school, so you can find every day all question and answer. Please use this file, so maybe when some tutor explain some stuff and do some lesson, the other can answer of your question, and the file remain until the end of the school. Okay, I think I said everything, so I leave to Paolo the stage.
Okay, thank you, Oscar. Okay, good morning again. My name is Paolo Giannozzi. I work at the University of Udine, close to Trieste, in the northeast. So geographically in the direction of the Eastern European centers that have organized this school. So I'm going to give an introduction to the basics of molecular modeling, materials and molecular modeling. So basic introduction to density functional theory and to the plane wave pseudopotential method. I guess some of you might find this introduction of relatively too simple, and others may not find that simple, but anyway, I'll try to cater to everybody. So this is the plan of the lecture. I haven't planned exactly the timing. I'll see if I manage to fit into into the time slot. It's a lot of stuff, so it can be discussed at will. But let's start also from the beginning. Let me move. Materials modeling from first principle, basically. And I guess you are here for first principle, that is from the electronic structure. So what we basically have to do is to solve the time-dependent Schrödinger equation for a system of electrons and nuclei, which is a rather serious endeavor. You have this Hamiltonian that have terms for both nuclei and electrons, and an interaction potential that includes electron-electron, nuclear-nuclear, and nuclear-electron interactions. And you have to solve the time-dependent Schrödinger equation, at least in principle. There is a basic approximation called the Born-Oppenheimer approximation that allows to disentangle this problem into two sets of problems. One, a problem of an electronic problem, so the motion of electrons, the electronic structure at given nuclear position. So you fix the nuclear position and solve the electronic problem. And then you get an energy which is known as the potential energy surface. So an energy is a function of the nuclear positions, and from this energy, this potential energy, surface energy, you find the behavior of nuclei from an Hamiltonian that has the nuclear electrokinetic energy plus this term as potential, as effective potential between nuclei. So the nuclear problem depends upon the electrons only via this potential, this energy here, this potential energy surface. This is the Born-Oppenheimer approximation, and it's a consequence of the large difference in mass between electrons and nuclei. It can be proven in a mathematical rigorous way, and so what in the end we are supposed to find, the important part of in this procedure, the most important piece of this procedure is the potential energy surface, so the energy, the electronic energy at given nuclear positions. We assume in the following, we always assume the Born-Oppenheimer approximation, and we also assume that you are dealing with the ground state, of the electronic ground state. Of course, this potential energy surface depends upon the electronic state. So there is a potential energy surface for the ground state, and there are others for the excited states. Now, so let's focus on the electronic properties, on the electronic problem, which is the difficult one. Now, we focus on the charge density and on this role in determining the ground state of a system. Now, there is a theorem called the Hohenberg-Kohn theorem, which dates back to a lot of years ago by now, well, so 60 years ago, which demonstrates something that apparently doesn't seem to be that useful at the first glance. That is that for each ground state charge density, there is a unique potential that depends upon the position of the nuclei, unique potential that has this charge density as ground state charge density. The formulation here actually is slightly more precise. There is a unique potential having an R ground state charge density, because not all charge densities actually are ground state charge density of some potential. Anyway, so this means that there is a one-to-one correspondence between charge densities or the ground state on the one side and potential having those charge density as a ground state charge density on the other side, which has some deep and far-reaching consequences. Like first one is that this means that the energy is uniquely determined by the charge density, the ground state charge density, and so it can be written mathematically as a functional of n of r. So to each charge density, there is a corresponding energy. And it's not difficult to see that this energy functional can be written as a sum of a universal energy functional, that is called F here in the slides, and of an interaction with external potential term, where V of R, and we have assumed here implicitly that the potential is local, so it's the potential or that the nuclei exert upon electrons. And another rather simple consequence, simple and quite obvious consequence, is that the ground state charge density minimizes this energy functional. Okay, this is very nice, but one has to figure out a way to write this energy functional in a form that is useful, because the Hohenberg-Kohn theorem only says that it exists. It says nothing about its properties. Actually, we know quite a bit about the property of the energy functional by now, so it's no longer a completely obscure object or completely unknown object, but it has some rather funny properties. Anyway, what is the way to bring this theorem to a usable form? So the idea is that since the Hohenberg-Kohn theorem holds irrespective upon the interaction between electrons, one can think of turning off the interaction between electrons, and the Hohenberg-Kohn will still be valid, and so a charge density will have a corresponding potential that has this charge density as ground state. So for non-interacting electrons, so we introduce this fictitious system of non-interacting electrons. We write the charge density as for non-interacting electrons as the sum of the square of one electron orbitals of the system. Here implicitly we assume, for simplicity, that there is no spin, so that the system is spinless. May assume that all the electrons have spin up and spin down and occupy the same orbital. Now, then we rewrite the energy functional by taking out the big pieces of the energy that we are able to write. So we write the energy functional as the kinetic energy of non-interacting electron, the term that appears here in the third formula, which, by the way, is not exactly the kinetic energy. The true kinetic energy of electrons is close to, but not exactly the same. So it's a term that you can easily write down. Then we can easily write down the Hartree energy, that is the interaction, the average electrostatic interaction between electrons. Then we can write there is a term of interaction with the external potential, and finally there is all the rest that we called exchange correlation potential, exchange correlation energy, and all our ignorance about the energy functional is hidden here. So the reason for this funny name, exchange correlation, comes from the comparison with Hartree-Fock theory, in which you have something similar. So you have a somewhat similar introduction of effective orbitals, one electron orbitals, and the energy is written in quite the same way, but with an exchange term, which is non-local. It's the complicated term called exchange. And the correlation energy is, by definition, the difference between the Hartree-Fock energy and the true energy. In principle, all this is exact, so the exchange correlation energy should contain both the exchange and the correlation terms. Now, if one minimizes the energy with respect to the Kohn-Sham orbitals, one finds with the constraints of orthogonality that have to be, that guarantee that the charge density has the correct normalization, the correct number of electrons. So you have, you find an effective Hamiltonian, which contains called Kohn-Sham Hamiltonian, that has the aspect of a one electron Hamiltonian plus with a potential that is a self-consistent, a function of the extended potential plus two terms called Hartree and exchange correlation potential that are respectively functional derivatives of the Hartree energy and of the exchange correlation energy with respect to the charge density. The Hartree term is simple. It's the potential, it's the electrostatic potential, and that depend self-consistently upon the charge density, which in turn depend upon the results, the Kohn-Sham orbitals, the Kohn-Sham eigenvectors, eigenfunction psi A. Alternatively, one can use the sum over eigenvalues, Kohn-Sham eigenvalues, one electron level, sort of one electron energy levels, epsilon I. And if one rewrites, writes the sum over epsilon I by taking the Kohn-Sham equations and manipulating a little bit, one finds that the energy is equal to the sum of eigenvalues minus a term that is a double counting term, because if you look at the sum of eigenvalues, you find that the exchange energy appears, this term here appears actually twice, so it has to be subtracted out. And also there is a difference between the exchange energy, exchange correlation energy, and the term, this exchange correlation potential term, that has to be accounted for. So this term is subtracted out from the sum over eigenvalues, and the correct term, the energy, exchange correlation energy term, is added back. Okay, all this, again, is useful only as far as there is a viable approximation for the exchange correlation potential that can be computed in a reasonable way, in a reasonably simple way. So, together with the Kohn-Sham equations, Kohn-Sham also proposed what is called the local density approximation. So the idea is that we have access to the exchange correlation energy for a model system that is called the homogeneous electron gas. So assume an electron gas of a constant density, of a given constant density. The exchange correlation energy for this system can be computed more practically exactly using techniques like quantum Monte Carlo techniques. And so we can write the exchange correlation energy as a function of the charge density, and we can make a weighted average of the exchange correlation energy, the given density, by assuming that at each point R, the exchange correlation energy is given by the local density and of R. Now, this doesn't look like an approximation, like something that can work well in materials which are composed by atoms, which means that they are not exactly similar to a homogeneous electron gas. So they are actually quite inhomogeneous, except more or less depending upon the kind of material, but in general, it doesn't look like the homogeneous electron gas is such a good model for materials, even if you consider the local density. So the next step, of course, is to take into account the inhomogeneity in some way by considering the gradient and the variation, local variation, spatial variation of the charge density. Now, this is not completely obvious. It's not completely simple. If the first attempt failed miserably, so if you just make what is called a gradient expansion, expanding to power of the gradients around the uniform case, it doesn't work, basically. But finally, it was realized that one needed to take into account some exactly known some rules in order to write a better functional, and a class of functionals called the generalized gradient approximation has been introduced, which depend upon the charge density, the local charge density, and the local gradient of the charge density. Now, these are the two basic functionals, actually the two basic classes of functionals, because one may define many different, slightly different local density approximation and many slightly different generalized gradient approximations. But anyway, all those approaches share quite common. They differ very little inside a given family of approximation. The results differ quite little. The differences between the different functionals are quite small, and they share similar behavior. Now, this for a rather unlikely system called, or rather unlikely system of spinless fermions, but we know that magnetization may be important in materials. So one has to think about a generalization to spin polarized materials. The simplest extension, which gives under the name local spin density approximation, even when it is not a local density approximation, assumes that you have a single quantization axis for spin. So you have a spin up and spin down only, and you have two charge densities, one for spin up states and one for spin down states. And the total charge density, of course, the sum of the two. And the energy, the exchange correlation energy, notably, is functional of the spin up and spin down charge densities, of both the spin up and spin down charge density. The spin up and spin down charge density are respectively given by the sum of our eigenvectors that have spin up or spin down. For the non-magnetic case, of course, you have the same eigenvectors and the same charge density up and down. And also, in the Kohn-Sham equation, you have the same potential for the spin up and spin down components, while in the magnetic case, you have a different potential for spin up and spin down electrons. Notice that I have here introduced in a stealth way another extension to the original density functional theory, that is the extension to system having fractional occupancies, which is important in particular for metals, in which with this extension you may have states that are partially occupied, and so this Fi and sigma are occupancies that might be in general fractional. Is needed for so this LSDA extension is needed for spin polarized cases, and the extension to fractional occupancy is needed to deal with metallic cases, with metals. Now, how does this work? Well, it works actually surprisingly well. The stability of atoms, the energy, atomic energies can be computed. One of the first calculations one may try actually look at how it works in atoms. And LDA tends to underestimate the energy of the atoms, but GGA gives results that are quite close to experimentally determined value. One may look also at the binding energy of small molecules. Binding energy of small molecules, that is the difference between the molecule and the two separated atoms. And here HF is Hartree-Fock, is not hydrogen fluoride. So molecules are in the molecules name are in the column. And one sees that typically LDA tends to give too high binding energy, while GGA gives results quite close to experiments. Sometimes even too weak. The oxygen molecule is especially remarkable. The experimental binding energy is much slower, much lower than results from LDA, and it's much closer to GGA. Hartree-Fock results are in Hartree-Fock without corrections are much worse than either LDA and GGA. So the typical application of, especially in the initial stage, the first application of DFT are in solids, because in solids it's especially convenient to work with DFT with respect to Hartree-Fock-like approaches. And what one sees is that results are actually quite good for, especially for semiconductors with wide SP bands, and for many metals, the results are quite good, quite closer to the experimental value in terms of equilibrium lattice parameter. That is the lattice parameter that gives the lowest energy. And in the order with errors that do not exceed 1–2%. Typically, LDA tends to give somewhat shorter distances and GGA somewhat higher distances, but it's more variable. And one can also see can also compute mechanical properties of the same materials and find that LDA tends to give bulk moduli that are typically a little bit too stiff, too high, while GGA tends to give somewhat softer materials. What is surprising is that even rather nasty materials like oxide seem to have quite good structural results. So one gets some reasonably good equilibrium lattice parameters and bulk moduli also for oxide. But what happens is that if one looks more carefully at the electronic structure, one finds that there are sometimes the electronic structure is not that good, sometimes it's seriously bad. Again, here some pictures that resume what I just said for lattice constant and cohesive energies of several of another class of ionic and covalent materials. There is a lot of, there have been a lot of studies about the performances of LDA and GGA and even other functionals beyond LDA and GGA. There's a infinite amount of literature that examines the various performances of those exchange correlation approximations. Now, LDA and GGA seem to make quite good work in computing, giving structural properties of materials, at least a large class of materials, quite nicely. What do LDA and GGA fail to do? What are the worst? When can they be used and when they shouldn't, or they can, but the results are guaranteed to be bad? Well, as I mentioned before, the exact exchange correlation energy and potential have a number of surprising properties. One of these is that if you extend the definition of the exchange correlation functionals to a fractional number of electrons, then you realize that the exchange correlation energy must have necessarily a cusp when it crosses an integer number of electrons. On the other hand, the exchange correlation potential should do what happens automatically in Hartree-Fock, that is, cancel the self-interaction of an electron with itself, because the Hartree term, if you look at it, it obviously contains an interaction of an electron with itself that shouldn't be there, but in Hartree-Fock it's also contained in the exchange term, and it's exactly cancelled. The exchange correlation potential in DFT should do exactly the same. It does, but not exactly. Now, this suggests that there is no way to write a simple function of the charge density, or even of the charge density and of the gradient of the charge density that can satisfy both conditions. And unfortunately, the presence of the discontinuity when the density crosses integer numbers, and the presence of spurious self-interaction are at the heart of most seriously shortcoming of simple DFT. So even now, after 60 years of DFT, still the search for a functional that correct the most obvious, most remarkable problems of simple DFT is an active research field, still a very active research field. So, in summary, it's DFT in the LDA or GGA form allows to deal with relatively complex condensed matter system in a quite cheap way. It's affordable, it's rather simple. And the difference between GGA and LDA is quite small. It doesn't cost that much more. You get typically excellent results for prediction of atomic structures, prediction of bond lengths, of the kind of structure, of the lattice parameters, of the cohesive energy. GGA is better than LDA, and of the vibrational property. There are, however, some problems, some known problems. So the famous gap problem. So the band gap, the difference between the lowest eigenvalue of empty states and the highest eigenvalue corresponding to occupied states. So the conduction minus valence band gap. Homologo gap, is called in molecular science, is a heavy underestimate of the true band gap. The presence of self-interaction causes a large number of serious trouble in materials with strongly correlated electrons, that is, with strongly localized atomic-like states. And finally, the so-called van der Waals interactions or dispersion interactions in quantum chemistry language is something that is simply not present in basic DFT with LDA or GGA, because it doesn't depend upon the overlap of the charge density. It exists only also in the absence of overlap. So it's a non-local phenomena that cannot be described by a functional based on local density or even local density gradients. So there are a number of advanced functional. You will hear about some of them in this workshop, in this school. First one is DFT plus U. So in order to correct for self-interaction, and one adds a sort of Hubbard-like term, a repulsive Coulomb interaction when two electrons sit on the same site, basically. And is the simplified version of the DFT plus U, of the plus U actually. Term. Sometimes it is referred to as LDA plus U. LDA not necessarily so. It can be any exchange correlation, and you add a Hubbard-like term, which depends upon the matrix of orbital occupancies computed by projecting your quantum state over a basis of atomic-like states, a manifold of atomic-like states that are strongly not localized. Well, it works quite nicely. but of course this introduces an adjustable parameter U, which is system dependent, and you can of course use it as an adjustable parameters, but it's not very nice as an approach. There are ways to compute from first principle. It is in a priori way to compute for a given system the correct value of U. It's the logic is sketched in this picture, in which one sees that the goal of the LDA plus U correction is actually to remove this curvature that is fictitious and to reproduce, to bring the functional, the energy functional as a piecewise linear term, as it should be. Now, you can extend the GGA by adding more terms, not only the charge density and the gradient of the charge density, but also the so-called non-interacting kinetic energy density that depends in some way. It depends upon the orbitals, upon the gradient of the orbital squared. And write an exchange correlation functional like this, which work actually quite well. They work quite well, these meta GGA, when they work, because the problem is that they are very numerically nasty, and sometimes it's difficult to get results from meta GGA. When you get results, typically they are very good. Then there are another big field of another big category of advanced functionals are the hybrid functionals. Hybrid functionals are in a way an admixture of DFT ideas plus Hartree-Fock ideas. So if one compares the Hartree-Fock energy with the DFT energy, one sees that the difference is the replacement of the exchange in Hartree-Fock with the exchange correlation in DFT. What one can do is to make to take some exchange energy, that is energy computed from Kohn-Sham states, Kohn-Sham eigenstates, as in Hartree-Fock, as in Hartree-Fock. That is, the exchange term is computed as in Hartree-Fock with Kohn-Sham orbitals. And you can add, you can take part of the exchange to be given by this Hartree-Fock-like term instead of the DFT term. So this means that you have to distinguish between exchange and correlation DFT, but this can be done on the basis of the behavior. Typically, the exchange goes as n to the as the charge density to the power 1/3. And the mixing term is also a parameter which can be changed with, can be used as an adjustable parameter, or it can also be chosen on the basis of some criteria. There are some criteria to choose the correct mixing parameter in hybrid DFT. Those kind of functionals give really nice results, especially in molecules. So the chemists, quantum chemists love them. The problem in solids is that, especially if you use plane waves, is that this kind of approach, computing this term, the term Hartree-Fock-like exchange, is quite heavy. The reason being that, especially if you have to delocalize the orbit, delocalize the basis sets like plane waves, you have to compute an enormous number of those terms, exchange terms. There are some technical tricks and some methods that allow to speed up in solid calculations of Weber-Hardit functionals, and particular, let me cite myself. Actually, the main author of this paper is Ivan Candineo. And in this paper, I explain how to use the adaptively compressed exchange idea and orbital localization to speed up calculations in solids for with a Hartree-Fock exchange. Finally, van der Waals. So, as I mentioned before, current simple LDA or GGA function don't contain the van der Waals forces. LDA actually contains an overestimate of interactions, so it actually contains something that may look like van der Waals, but it isn't. It doesn't have the same origin, it doesn't have the same behavior of distance between atoms. But it is possible, and it has become feasible, technically feasible, thanks to some computational advances, to write down functional that is non-local, an energy that is non-local. You see the non-locality here in this kernel phi of R and R prime. And they work quite well. Sometimes they overestimate van der Waals interaction, sometimes they underestimate, so it depends a little bit. The alternative approach to DFT is to add it simply as a semi-empirical correction. You choose some GGA and you add what is missing under the form of a typical 1 to the R6 distance behavior and a coefficient that is proportional to the product of the polarizability of the two atoms. So it's not an electronic structure term, it's a term that depends only on the kind of atoms and their positions. It works quite nicely also. It's not really first principle, but anyway, it can be a viable way. And then there are some intermediate cases, let's say, that are not really semi-empirical, not just adding a semi-empirical correction, but adding a not so empirical correction in which those coefficients are computed, those C6 coefficients are computed from first principle, from the electronic structure, that derived from the electronic structure, so Tkachenko-Scheffer, or the exchange hole dipole model. All these cases are implemented in quantum espresso. Now, okay, I'm going too slow. So how do we find? So we have, let's say, we have our method, our DFT. We choose a functional, and how do we find the ground state? There are two basically ways that are quite equivalent to go to the ground state. One is simply following the Kohn-Sham idea and solve self-consistently, that is, at fixed potential or fixed charge density, the Kohn-Sham equations, which means diagonalizing a matrix. If you project the Kohn-Sham orbital on a basis set, then you end up with a diagonalization in which the matrix, however, depends upon the solution, so you have self-consistent, so you have to reinsert the solution back into the charge density and into the Hartree and exchange correlation potentials. the orthonormality constraint that have to be respected between the Kohn-Sham orbitals automatically come out automatically during the diagonalization. An alternative way is to observe that what we actually do with the Kohn-Sham in the Kohn-Sham equation is to find the minimum, is to minimize the energy. So an alternative way is to minimize the energy directly. That is, you expand again your orbitals or your Kohn-Sham orbitals into some plane, some basis set. So you have coefficients, and you write the energy as a function of this coefficient with orthonormality constraints that have to be enforced explicitly. So you minimize this auxiliary functional of the energy. So the energy as a function of the Kohn-Sham orbitals minus the term, the Lagrange multiplier term that ensures orthonormality. So self-consistent diagonalization versus global minimization. These are the two aspects, the two typical ways. The first one is the one used in most of quantum espresso, but there is also the second one that is sometimes very useful, and it's used in the Carparinello code. Now, so this scheme of what happens, self-consistency, self-consistent diagonalization. Those two aspects, those two approaches look rather different, but they aren't actually. At least they aren't, because the main ingredient is invariably the same. So the main ingredient is always the product of the Hamiltonian matrix times the Kohn-Sham orbitals. This is because if you use iterative diagonalization, I'll briefly mention it later, this is what you need. This H, the Kohn-Sham Hamiltonian times the Kohn-Sham orbital is what you need. If you use global minimization, what you need are gradients of the energy with respect to the Kohn-Sham orbitals. And these gradients are actually nothing but they are related to the same quantities, Hamiltonian times Kohn-Sham orbitals. Now, in the case of the self-consistency, self-consistency can be sometimes problematic, actually. Can be problematic because simply reinserting, if you simply reinsert what you get as a charge density at the previous step into the next step, you have no guarantee that this procedure will reduce the error. That is, this procedure will actually cause the error, that is the difference between the current charge density and the true final charge density, will be reduced at each step. Actually, what happens is that there are components of the error, typically so-called high-frequency components, or those with large G in a reciprocal space approach, reciprocal space description, that are quite quickly fade away with this procedure, with the self-consistent procedure, but low-frequency components tend to be much slower in to be reduced at a much slower rate, or not to be reduced at all. So those low-frequency components of the error often appear, for instance, if you have a long elongated supercell and correspond to charge density, charge sloshes, that is charge going back and forth along the system. Now, there are some algorithms to deal with convergence issues, self-consistency convergence issues. The basic is the so-called simple mixing. So you don't put the entire output back into the input, but you put a bit of it, a part of it, and you mix with the previous input. And this guarantees that if the mixing factor alpha is small enough, guarantees convergence. There are better algorithms, more sophisticated algorithms that takes into account a number of previous steps, and from the previous steps, from the input and output at the previous step, they find a combination, linear combination that minimizes the error in the next step, and then add a mixing term. They typically work well. Sometimes they are problematic. So how do I converge my job as a typical question on the quantum espresso mailing list? More often than not, the reason why your job doesn't converge is that the data is not what you think it is. So your system is not what you think it is. There are some errors in the data, but sometimes there are some nasty cases, especially magnetic cases, in which convergence can be quite problematic. Now, once you have reached the self-consistency, based on some reasonable criterion, you can compute the total energy of the system, and this is what you need. So then it is a function of the nuclear positions. Now, you can also compute not only the total energy, but the gradient of the energy with respect to nuclear positions. So this can be done based on an extension of the Hellman-Feynman theorem, an equivalent, let's say, an equivalent of the Hellman-Feynman theory for density functional theory. The Hellman-Feynman theory says that all you need in order to compute the forces is actually the explicit gradient of the explicit expectation value of the explicit derivative of the external potential acting on electrons. Now, in DFT, you have something very similar, because the derivative of the energy with respect to the nuclear position have an explicit term that is this one, is the integral of the charge density times the explicit derivative of the potential with respect to nuclear position, plus an implicit terms that contains the derivative of the charge density with respect to the positions, which is something that we don't know at the end of the self-consistent calculation, something that can be computed with linear response. I'll show in 2 days how to compute these quantities, this derivative of the charge density with respect to the nuclear positions, but it's something that requires a specialized calculation, so it's something like quite tough to compute. But the point is that we don't need it, because this integral in the ground state vanishes exactly, because this derivative of the energy with respect to the charge density is actually constant. So the integral of this variation of this derivative is 0, because the charge density cannot change. Okay, this is a sort of a very simplified derivation. So the message is that once you have the electronic structure for the ground state, you can easily compute the Hellman-Feynman forces, at least in principle. Then there are some subtleties, but I'll come back to this later, which means that in the end you have the energy. You may compute the energy as a function of nuclear positions, and then you can compute also the forces of the gradient. So you can easily find the minimum. So you have the energy as a function of the nuclear position, which has a minimum corresponding to the ground state, the global ground state of the system. it may have also local minima that correspond to metastable states, but this is finding the minimum and the global minimum and local minima becomes it's a well-defined mathematical problem that unfortunately doesn't have a unique and ultimate solution, because you never know that you are really at the lowest minimum. You can never know. But anyway, one can use machinery, mathematical machinery, for minimizing functions, knowing their gradient, the gradients with respect to variables, minimize functions of many variables. Or you can even compute, and also do molecular dynamics. So you can do molecular dynamics and recycle the machinery of classical molecular dynamics. But unlike classical molecular dynamics, you have forces that are computed from the electronic structure and not from a model of interatomic interactions. Now, the difficult part here is the solution of solving the quantum problem at fixed potential or fixed charge density. So the hard part is this, and it is done by projecting over a suitable basis set our quantum orbitals, and this brings to a circular equation, so-called. It is a matrix equation that is well known. So it's probably it's reconduced to the diagonalization of the matrix, or a generalized diagonalization. So a generalized problem in case you have your basis set is not orthonormal. Now these are problem that is very well known, but in practice it's not the way. We don't use actually well-known algorithms of diagonalization algorithm, because they would require to store the entire Hamiltonian matrix, and this is something that typically we cannot afford. So one uses actually iterative diagonalization. Now, basis sets, which basis set to use depends upon which party you have subscribed to. There is the party of localized basis set, atom-centered localized functions like Gaussians, or a linear combination of atomic orbitals, or linear Markov orbital. And then there is the party of plane waves, or delocalized basis set like plane waves. One might also consider there are also mixed cases that are somewhat intermediate at the LAPW, organized augmented plane waves. You have localized plane waves into a sphere plus augmented by plane waves. Localized orbitals, atomic orbitals in a sphere, and outside the sphere you have plane waves. Anyway, each basis set has its advantages and disadvantages. So in particular, plane waves are, well, you need many more of them typically than localized basis set. Atoms, well, of course, are better described. Systems of atoms are better described by atomic-like functions than by completely delocalized functions as they are, as plane waves are. Moreover, plane waves are bound to a specific periodicity. So you have a periodic system, and this defines automatically a set of plane waves, or plane waves for your system. If you don't have periodicity, you have to invent one. This is not true for localized basis sets. On the other hand, there are some advantages in using plane waves. One is it's easy to evaluate the quality of the convergence by just increasing a single parameter, because the so-called cutoff, or the kinetic energy cutoff, because plane waves are complete in the limit, in the infinite limits are complete, while localized basis set may become over-complete, so more than complete. And they are quite straightforward to use, and they give access to some algorithms that are very powerful and fast, like a fast Fourier transform. And the calculation of forces is straightforward, even if the basis set is incomplete, which is not true for localized basis set. There is a term in case of incompleteness of the basis set called Poulet forces that has to be taken into account if you want to compute forces in accurate and precise forces. Now, so periodicity. Periodicity is, so let's focus now on crystals, on infinite perfect crystals. So it has a periodicity that is defined by a unit cell, periodically repeated unit cell, which corresponds to a lattice of translation of translational vectors. So this basic solid state physics. So translation vectors are linear combination of three primitive vectors, R1 called here R1, R2, R3, with integer coefficients. And moreover, you have to define the atoms in the basis of atoms of atomic positions in the unit cell, which must not be necessarily inside the unit cell. The definition of the unit cell is somewhat arbitrary. You can displace the unit cell as you will, basically. But anyway, the number and type of atoms in the basis is well defined for each crystal. And then from the lattice vectors in real space, you can define the reciprocal lattice of vectors defined by these constraint. So the reciprocal lattice vector, any reciprocal lattice vector, scalar product with any lattice vector gives an integer number of 2 pi. So once you have, if you have this R1, R2, R3, you can automatically define the G1, G2, G3 corresponding to this R1, R2, R3. This is something again that comes from basic solid state physics. What happens if you don't have a periodicity? So if you have a perfect lattice, a perfect crystal, then you have a well-defined periodicity. You may have different structure with different periodicities. What happens if you don't have exact periodicity or no periodicity at all? That's the case, for instance, defect in crystals with a defect. So a case of surface in which you may have periodicity in 2 dimensions and not in the orthogonal direction. It's a case of alloys in which you may have some disorder in composition. In the case of amorphous materials in which the crystal structure is sort of present at the local level, but there is no periodicity anyway. So the crystal, the sort of distorted crystal, or so distorted that you don't recognize that there is a crystal at all, or even liquid. So you may want to study liquid water. It's a very interesting material for a number of applications, or molecules, or large molecules known as clusters, none of which has exact periodicity. So one has to introduce a suitable periodicity, artificial periodicity, via so-called supercells. So the supercell, the geometry of supercell depends upon the type of system you are studying. So for instance, if you have a molecular cluster, then you have to allow, you have to define a supercell that is large enough so that the periodic images of belonging to different supercells do not interact, or their interaction can be negligible. How big a supercell must be is something that depends a lot upon each specific case. There are some techniques to minimize, that allow to minimize the spurious interaction between different cells, so-called Martina-Tuckerman, of the Octane technique that, however, is not implemented in quantum espresso. For a defect in a crystal, you consider a supercell that is large enough to minimize, to make the spurious interactions between different periodic replicas of the defect negligible. How can this be verified? Well, you have to look how, okay, it depends a lot upon the specific case. You have to look at how much and how far away from the defect the crystal changes its structure, and you may have a look at defect-related levels, and if they show a significant dispersion in K-space, it means that they are a little bit too close. Of course, all this becomes much more difficult if you have charged or dipolar system, in which interaction, the spurious interaction becomes much longer range and has a longer range. For surfaces, you use typically so-called slab geometry. So you have true periodicity in 2 dimensions and the fake periodicity along Z. Again, you have to leave enough empty space between the periodic replica so as to minimize the interaction, to have minimal interactions between the surfaces. And also you have to go to reach inside, to go inside the slab, deep enough to reach a region of atoms in which that do not feel, do behave reasonably as in the original crystal. So you take a crystal, you cut a slice, and you take a slice that is thick enough to reproduce the behavior of the crystals inside the slab, and distances with a sufficiently empty state between the slices so that the slices don't see each other. For alloys, amorphous materials, liquid, then you have to consider the bigger, of course, the bigger the better supercell. That you have to find a supercell that gives a reasonable description of the physical properties and that doesn't introduce spurious correlations between what happens in a supercell and what happens in another. In a real liquid, for instance, there is no correlation between atoms that are sufficiently far away, and this must be also and so the supercell must be sufficiently large to ensure that when the correlation between spurious correlation due to periodicity is doesn't affect the physical property. Notice that there is no difference between between a supercell and a cell. So they are the same. Simply a supercell is a cell with a lot more atoms than usual. And the difference between supercell and cell is simply quantitative, or it depends upon the system that you have that you are working with. Now, in the case of crystals, you also have periodic boundary conditions, and you have block states. So your states are conscious state are classified with a band index and a wave vector index and block vector index. Now, at each wave vector, at each block vector, you have a set of plane waves that are uniquely defined by the formula shown here as the exponential of I times k plus g, where k is the block vector, the scalar product of R, and up to a g vector. So g is a vector of the circular space, up to g vector, and k is a block vector, and g vector, such that the kinetic energy of those waves are smaller than a given cutoff. Cutoff is traditionally given in Rydberg. Now, the advantage, so now the plane waves, so allow to write the Kohn-Sham equation as Fourier components, basically. So what you have is your Kohn-Sham states are described by a set of components of a plane waves that are basically the Fourier transform of the plane wave of the Kohn-Sham orbitals. Now, one big problem with plane waves is that they are not really the most suitable basis set to reproduce functions that vary very quickly in a small length scale, like, for instance, core valence. So atomic core valence are very concentrated around the nucleus, and so they vary very quickly on a length of scale that is quite small, order of fractions of Bohr radius. And since valence states are orthogonal to core states, also valence states close to the nuclei have a strong spatial variation on a length scale that is very small. So this means that in order to reproduce those features at close to the nuclei of Kohn-Sham orbitals, you need a disproportionately large cutoff. So you have to go to very high Fourier components of very large modulus. This actually, you may say, okay, I threw core states away and keep only valence states. Yeah, but the valence states still have these oscillations. So what is done is to introduce a pseudopotential. Pseudopotential is a smooth effective potential that reproduces the effect of the nucleus plus core electrons on valence electrons, but the valence electrons are actual pseudo-valence electrons. That is, they don't have the oscillations, the fast oscillations around the nucleus. So this is what the pseudopotential is supposed to do. The quickly oscillating parts close to the nucleus are taken out, are replaced by a smooth version, which, however, in the case of so-called non-conservative pseudopotential, must ensure that the total charge density, the charge density contained be radii that are distances from the nucleus that are smaller than some cutoff radius, that is more or less at the maximum of the outermost maximum of the atomic planes, atomic states. The charge density has to be the same. It's a little bit late now, so I'm cutting short here. Basically, the pseudopotential is something that should allow to reproduce the results of all electron calculations and with plane waves, or with whatever basis set, actually. So pseudopotential can be used and are used also without plane waves. It's not needed. But the important point is that pseudopotentials are first of all atomic-like objects, so they depend only upon the specific atom you are dealing with, and their properties also are typically atomic-like. They are localized functions around the function that are localized around the core state of the core states of the nucleus of the atoms, and they're a sort of something that you choose, you test. It's very important to test pseudopotential for correct functioning. They depend also on the exchange correlation function. So at least in principle, you should use a pseudopotential generated from atomic data with the same pseudopotential, with the same exchange correlation function that you are using in the calculation in solid. This is not always possible. You find much information on the website of Quantum Espresso on how to select pseudopotentials and where to find pseudopotentials. So by now there are pseudopotential tables that are quite reliable, that are heavily tested. And there have been a lot of effort in the community of electronic structure calculation in recent time to test pseudopotential, in particular to test that pseudopotential do give results that are as good as all electron calculation. Electron calculation means a calculation in which both core states and valence states are present, and the true Coulomb potential is used for atoms. In particular, we mentioned this paper that is a collaboration with many people, including myself, in which it is shown that a modern table of pseudopotential actually give results that are comparable in quality to all electron calculation. So this is a short summary of the plane wave pseudopotential method. Actually, it's the same that I showed before. Once you have, so this is the inner self-consistency loop, and once you have computed the inner self-consistency loop, you can compute, you have solved the inner self-consistency loop, you can compute energies and forces and whatever you like. Okay, this technical stuff that's not necessarily important. Just very quickly, since we have in solid, you have periodicity. even if sometimes it's a fake periodicity, you have, when you sum over Kohn-Sham orbitals, you have a sum over key points. So the sum over key points may be quite critical in some cases. Of course, in some cases it is not. So for large supercell, you just take k equals 0, and that's okay. Otherwise, of course, especially for metals, you need to sample the Fermi surfaces with a quite fine sampling, and you need to broaden the states in order to be able to perform cell consistency. And finally, when you have done the inner loop, linear SCF loop, then you can compute forces in addition to energy forces, and then you can use forces to move ions and perform molecular dynamic calculation or structural optimization. It is to find the minimum energy of the structure of the minimum energy. Something that now it's very latest, the very last thing I'm saying today is that in periodic systems there is a distinction between the atomic displacement of atoms in a unit cell and at fixed cell, and atomic displacement that imply a change of unit cell. So these are not, cannot be treated in the same way, because in one case, a fixed cell, the periodic boundary condition remains the same, the basis set remains the same. In the other case, the basis set changes, periodic boundary conditions changes. And in that case, you have to resort to stresses instead of forces to see what happens, what atoms want to do. Stresses can be computed with, there is an analogous of the Hellman-Feynman theorem for stresses. Okay, this is a simple case of, simplest case of structural optimization that is done by computing the energy versus volume curve and fitting to an equation of states. Okay, I'm afraid that I've run out of my time, so let me stop sharing.
Thank you very much for the talk. So now we should have 15 minutes coffee break, which was supposed to start at 10 minutes ago, but that does, I think it's okay if we start now at 10:55. So hello back. I hope you have enjoyed your coffee, and we should now continue with the program. Oscar, can you take over?
Yeah.
Thank you.
Hello to everybody again. Okay, I'm Oscar Baseggio. I'm from SISSA in Trieste. And now this is the first section, the first hands-on section. Now I want to share my screen. Yep. Okay. Oh, wait. Yeah. Okay, I have some slides, but really don't follow this. Okay, for the day one, we will explain you how to install and compile Quantum Espresso, the first basic run of PW, and then some tools for the post-processing. So I will show you how to plot the molecular orbitals and the density of states and the band structure. In the afternoon, Anton Kokalj show you the other system, for the bulk system, and how to converge testings, the problem with the metals and ultrasoft pseudo potential and spin polarization. Okay, first to start with the exercise, some utils information about Quantum Espresso. This is the website of Quantum Espresso. Here you can find everything about the codes, the download pages, the documentation, all the past tutorial. You can find a lot of stuff in this website, and in particular, this is the useful links that I share with you. The Quantum Espresso website, the download page to download the latest release of Quantum Espresso and documentation and so on. Then also there is a forum for the QA users. So if you have some question, or maybe you can find here. And also the mailing list for if you have a question about some problems, some bugs of the code, you can write on the user mailing list that someone reply you as soon as possible. So go for the first exercise. Okay, so move to the virtual machine, open a terminal. You can find the button in the app of the virtual machine. I will make all the exercise on Barbara. So first of all, I want to log into Barbara. I have my user. Also, you have your user, and update your SSH keyword like in the tutorial. I think you already have the access to Barbara. So now we are in the Barbara cluster. So I suggest you for this exercise to use the scratch area, because it's easier for us to find your directory on your Quantum Espresso version and the exercise, so we can help you faster. So also we have a work area common to everybody, is MNT proj free. The name of our project is this one, DD 23116. In this common area, you find a safe version of our code that we use in this school. So you can find Quantum Espresso, the last release of Quantum Espresso, already compiled for CPU, for GPUs, PWTK. I don't know why, because, but don't explain you. We'll talk with you about PWTK and also the pseudo-dir, but I show you later the pseudo-dir for the Quantum Espresso. Now we move to first of all, we move to the scratch area. So our scratch area is scratch project, and the name of our project again, DD 23116. Here you can find some directory. This is mine, but today I create another one, so you can find you can follow me in each passage. So now I want to create my directory where I want to compile quantum expression, and I will do the exercise. So create my directory, and I call with the name of my user. So this one, DD 23 116 minus 077. So now move on my directory. So also you create your directory with your user, so it's easier for us to follow and for you to find your directory. If you don't remember your user, you can find here. Okay, now here we have to clone the Git repo of the school with contain all hands-on exercise. You find the name of the repo in the HMD file. Here you can find there are a lot of stuff. You can find where is lesson material. You can copy this. Oh, okay. This. Okay. Move. Come back to the terminal and use the command git clone. You put the link of the Git repo. Press enter. And you copy all the material of the school. So now, if check, you have materials, directory materials, and here you can find all the days. In the virtual machine, is already updated. So here you can find you have to clone on the Barbara. Okay, now move to the day one directory and move to the example 0, the installation for the first exercise. Okay, now you can see here a GZ package of the last release of Quantum Espresso. This script are the script to compile on Barbara, and also you can find a README file. Each directory contains a README file with the information and the instruction to do the exercise. So if I try to open the README file, you can find here the instruction to do. No? So you have to untar the QE package to extract the program, and then they follow the instruction to compile the Quantum Espresso. So first of all, we have to copy this command and untar the Quantum Espresso package. Okay, you can check. Now you have the directory with the Quantum Espresso. So now I come back, wait for the okay. Okay, I think I said everything. Come back to so move to the Quantum Espresso directory. Here you can find a lot of directory. Each directory contains one program or one library of the Quantum Espresso. So the main driver is the PW code. So if we go inside of the PW directory here, you can find some other directory. In the directory SRC, you can find the source of the code. If you are interested in develop or check the code, so you can find it. Not, it doesn't matter. I want you focalize you on the doc directory and the examples directory. The doc directory contains all the documentation about PW, the user guide, and also the input information of the PW. So this is useful so for the new user, or if you want, don't remember the name of some variables you can find here. In the examples, you can find a lot of examples of the calculation that you can do with the PW. So if you want to try some stuff, maybe you can find here an example similar to use. So come back to the directory. Now we want to compile Quantum Espresso. So before start with the compilation, we have is necessarily have some libraries. First of all, you need a compiler to compile the Quantum Espresso, an MPI library. This is necessary. Then you have here, we have loaded some other libraries, the math libraries, FFPW and libxg. It's not necessary, but it's better using the libraries that you have in the cluster, respective with the Quantum Espresso already has inside. We choose this library, this module for this school, because if you check the module that have Barbara with the command module v available, you can find a jungle of module, so we can choose this stuff because okay, it's work for the example that we use it. And also Barbara already have some Quantum Espresso installation. If you check module AD Quantum, maybe. So you can find here all Quantum Espresso version compiled on Barbara. Here you can find also Quantum Espresso for GPUs and CPU. Now I will show you how to compile the CPU version, but it is almost the same. You have to load the different modules and put some flags on the configure line, but it's all documented. And if you have some problem with the specific cluster, maybe the staff of the HPC Center can help you to compile some codes, not only Quantum Espresso. So if you okay, move to the slide, I think. Okay. To compile Quantum Espresso, you can use the make or CMake. I will show you today the CMake version, but it's indifferent. In the documentation, in the user guide, you can find everything for the make building and the building with the CMake. It's completely the same. You can use what do you want. in the script, you can find in the script, if you check the script, choose CINECA, you can find here the module loaded, Intel compiler, Intel MPI, Intel MKL, FTW, and libxg, and also CINECA for the CINECA. This line is to run is a batch script to run on Barbara. I think you already know how to run on Barbara, or maybe not, but it's easier. Here you can find out how many nodes you ask, how many tasks and CPU per task. Here is 8. Okay. The time, the maximum time, your account. This is our project. The partition now is a CPU partition, and not the GPU partition. Barbara has a CPU and GPU partition. And this is the reservation that we have for this school. Attention that during from 9 a.m. to 5 p.m. So if you try this evening the exercise, comment this line. If not, the exam, the run doesn't start. So move to the Quantum Espresso directory. Now I use CMake, so I have to create a build directory and go inside. Now I copy the script that you can we saw now, and then I have to run the script with this batch. The Slurm generate an output file that you check until during the command. You can see here everything starts to Quantum Espresso compilation. So now takes I think 3-4 minutes. So if you have question and if you try to run, if you have problem, write on HackMD page or write your hands, or but if you have some question, or maybe if there are someone in the breakout room, maybe I lost the breakout room, sorry. Okay. If you have question, you can write on this part of the hands-on of the day one. Okay, if you have success, you can find in the bin directory all the binary execution for all program inside the Quantum Espresso. In this morning, we will use the pw.x and then pp.x, the post-processing, the DOS.x for the density of states, and bands.x for the band structure. So the last things to do before to move to the other exercise, you can find in the Quantum Espresso directory a pseudo directory. We have aside some pseudo potential. But if you go to the test suite, this is a suite to test the quantum expression for the developer. But if you do this command, make pseudo, takes 50 seconds, 20 seconds to do. And this command generates all the pseudo potential that the test suites uses. And also we use some of this for our exercise. So now you go back to the pseudo dir, and you can find here a lot of pseudo potential. So if you want to use, if you want to find some pseudo potential, do you know that the quantum espresso already has some pseudo potential, a lot of, but for the test suite. So we will use this pseudo potential for our exercise. Okay, for the example 0, I think I have done everything. Before to move to the exercise 1, I think I give you 10 minutes to do the quantum espresso compilation. Please ask some question if you have problem. If you check, if I check now in the Scratch directory, please create your directory here and try to do the exercise 0. And please tell me if you have some problem. How is it going? No one? Okay. Oh, no. Someone had success to compile quantum espresso? No one? Silent.
Sorry, can you
Yeah.
share the history of your executed commands?
Yeah. Maybe. Okay, this is the for a script, for the CMake script. This is the Antar, the quantum espresso package. And the, okay, this is the for clone the Git repo. CMake. Okay, maybe I copy. Copy the command on. Okay, I think I have copied all the command. Attention. Okay, enter inside the one day one and the example 0 directory. Okay, I think I move on the exercise 1. The exercise 1 is the basic run with the PW, and first of all, we try to describe a molecule with quantum espresso. So how to said before, we using the localized basis. So we have to put the molecules in the big box, like in this figure. We try to describe the benzene molecule. This box is a little bit small, but for the purpose of the speed of calculation, so we have to wait a lot of time, and then we will try to plot the molecular orbitals for the benzene. But now start with the SCF calculation, the self-consistent calculation of the benzene. So move to the example 1 directory. Also here you can find what's happening. Look, I have some problem with you. So, okay. Try with the stomach. Okay. Here you can find in this directory, again, in the README file. If you check the README file, you have all the instructions to do this exercise. Okay. So first of all, we will use PW to do the SCF calculation. Again, we use the post-processing calculation to compute the module of C to plot the molecular orbitals. And then we will use the X-Reason, that is a tool, a very powerful tool to visualize the molecules and orbitals and structure of the quantum espresso input, output, and others, and a lot of things. And then we will plot all of the molecular orbitals. So before to run the quantum espresso, the PW.x, check the PW input. The input of PW is structured in block. You can find here a control block, a system block, so electron, atomic species, and atomic position, and the key point. So each blocks, each keyword you can find in the documentation. You also try here in the RCMD, I think you can find the quantum expression page, okay, but if I check, if I try to find input w.x, you can find in the Google, this page contains all the information about the input of W. You can find all the blocks, control blocks, system block, electrons, ion cells, a lot of stuff. Okay, so it's impossible to remember everything. So you can go here and you can find all the keywords and so to run PW.x. So first of all, control system is a control block. It's to define the environmental variables. So The prefix is the name, the first name to add to the output and the input and the file and so on. And with function, you can find a lot of files that start with this name, dot, something else. You can find here the pseudo-dir variables and the out-dir keyword. Pseudo-dir define the directory where you can find the pseudo potential. So go to the pseudo-dir that I showed you before and copy the path. So go back to the example 0. If you don't compile Quantum Espresso, don't worry. There is a Quantum Espresso with the pseudo-dir on the workspace that I showed you before. So it's MMT, and maybe you can find also in the slides that you can find in the. This is the path. I use this, okay, to show you. It's indifferent. You can use your Quantum Espresso pseudo-dir in the example 0. You can use this one, but you can define where you can find the so I modify here W zin. You can find the pseudo-dir path, remove the comment, and put here the path in. So the directory is the pseudo. So this is the path of the pseudo-dir. The out-dir is the directory that PW generates to put the output file. So maybe I choose a name like PMP. And PW generated this directory and put all the output file on this one. The system block is the block that defines the system. Okay, this is the benzene. You can find here the characteristic of the cell. I don't remember which cell is with the EBRAV equal 6, so I go to the input page. You can find the system, EBRAV, click on EBRAV, and here you can see all the Bravella-TIS index that are already implemented in Quantum Espresso. So as a lot, so I don't remember really. The 6 is the tetragonal cell. So we use a tetragonal cell to put the molecule of the benzene molecule. This is the dimension of the box. A capped wave function and the capped rho is the cutoff of the energy and the density. Also, if you don't remember, go to and you can find here, oh, it's a lot. Go left, a cut. You can find here that wave function. The kinetic energy cutoff in Rydberg for wave function. Okay. The number of atoms is 12, 6 carbon, 6 hydrogen. And then the number of the bands that we computed, 16 in this case. The atomic species that we use is carbon and hydrogen. And you can find here the pseudo potential that you can find in the pseudo-dir of quantum espresso there. And also you can find here the atomic position. Okay. Okay. Saving the file because I modified the path of the pseudo there and the outer there. Before starting, maybe I'll do something. No, okay. Okay. So go to run the first PW. So here in the directory, you can find the run PW script here. Run PW. Go to run pw.sh. This is the same batch, the same script that we used before. You can see here H CPU, so 8 tasks, 1 CPU per task. The account, the project, CPU partition, and the reservation. This is the same model that we compiled before, that we used for compile the Quantum Espresso. But in the end, you can here use this as run and the core. This is for the Barbara variables. You can find here the bin QE path. So here you have to put the binary path of the where the script find this binary. Maybe I already have copied the last path. No, okay. Yeah, because I select this one. Maybe I use now I using my path that I compiled before. So I remember is example 0 installation / QE-7.3.1 / build / bin. If I write correct, you can find it. If not, compare an error, a crash error, I can find the line. So now I prepare the script, so go to run the PW for the benzene. Maybe I check, start, create a TMP here. So I call TMP and created the TMP directory. So if you choose another name, create another name directory. Maybe that's finished. Okay, you can check the output. You can see on the the first part of the output of the PW. You can see here the information about Quantum Espresso. You can find also the Quantum Espresso website, the version of Quantum Espresso we use, the parallel information. Now we use 8 processor, 8 MPI. Thread is for the OpenMP that I'm using today. So the memory, okay, this is the other information. Also the pseudo potential that we used here. Gamma point specific algorithm, because we compute now the molecule and not the periodic system. The other parallelization info, the dimension, the system. This is all the information that we put on the input. So you can see the Bravais index, the dimension of the boxes, the number of atoms, the type of atom, and so on. The crystal coordination, the crystal axis, and the reciprocal space. The pseudo potential, here the carbon, here the hydrogen. The atomic species, the Cartesian axis, and the number of key points. This is gamma calculation, so you have only one key point. And then start the self-consistent calculation. You can see here in each iteration the energy, in the end the total energy, and the estimated SCF accuracy, and the timing of the CPU. This calculation is very fast, so 6, 7, 8, 10, okay. You reach the convergence in 10 iterations, okay. So the finish, and you can see here all of the bands that we asked to compute. So we asked to compute 16 bands, so you can find the energy of the 16 bands. You can see the highest occupied and the lowest unoccupied level. So the minus, this is the highest occupied and the lowest unoccupied. Total energy, the singular contribution of the energy, and in the end, the timing table of each subroutine, how many time you need to compute how many calls. Okay, and in the end, you can see the timing, the total timing, and the job done if you have job done. Okay, in TMP directory, you can find an XML file which contains all the information about the system and the output. And the benzene save, you can find other information like wave function, the pseudo potential, charge density, and so on. You can see here the prefix that we use, prefix benzene, so you can create the PW create benzene dot something files and so at this point we have to compute the module of psi to plot the molecular orbital, and for this we use npp.x program. So if you check the pp input, it's simpler than PW, but what is important is that the prefix and the out there have to be the same of the PW1, because PP try to find the file and the directory with the result of the PW calculation. So the prefix is benzene, so it's the same, and out there here is comment, so we have to remove the comment, and the perfect is the TMP. If you choose another name, you have to modify this name here. This is the file plot where the output of PP. And also the plot of the generate a lot of file with this extension in the end. Okay, move to the script for the PP, for the pp.x execution. Also, here you can find the same script, but here we use only one processor because the post-processing is very fast. So typical run the post-processing program like PP, DOS, or bands in Syrian because it's very fast. Okay, I'll show you here. And also you have to put the same path for the binary. I don't maybe I copy now on this one. Copy the binary path in IP. Put here the binary path and run the PP, but it's very fast. So you can see here generate some files. Generate one file per band. You can see here the name of the site, the module of site that's create. So you can see here benzene K001, the number of K points. So this is gamma, so we have only one K equal 1. And this is the number of the bands. So you can see from the band 1 to band 16. Okay. Okay, done. Let me check. Okay. Okay, PP to plot this. Okay, now generate this. Now we will use XCrease then to plot this XSF file is for XCrease then. So for these things to visualize a plot or molecule or molecular orbital, usually don't run the visualization on the cluster, but in your laptop. So we have now the virtual machine with all of tools already compiled. So we copy this XSF file on the virtual machine, on our virtual machine, and use it. And we will use the XCrease then on the virtual machine. So open another terminal. Move. This is I move here in the day 1 directory, example 1. Okay. Here I didn't have I don't have the file that I generate on Barbara. This is Barbara. This is the virtual machine. So I will use the scp command to copy this XSF file to the virtual machine. So maybe I have an SSH. Okay. Or maybe I already copied yesterday some stuff. So it's the same of the SSH. You have to put, maybe increase. Oh. SCP minus E, the public key, and then you copy from, this is the copy from virtual machine to Barbara, and I want to copy from Barbara to the virtual machine. So this is my user, but not, this is not the correct path. I have to user // and copy this path with the PVD. No. Okay. And make slash point set and point to copy with the same name. I hope maybe no. Okay. Now it's still copying the file on the virtual machine. Very fast, it's only 65. Okay, here you can find, now we have on the virtual machine the XS file. So now I tried with one of these, open one of these with xscript, like this command you can find here, xscript -- xsf, the extension of the file, and then the one of the file you can choose -- xsf, and then choose one file. Okay, I choose one. Choose this one, but you can choose what do you want. Okay. Now xscript, sure it is like this, is open the interface, the visualization. Here you can find our benzene in the box. With the left point of the mouse, you can rotate. You can scroll to increase. But now I want to plot the specific molecular orbital. So I think this is good for this. You have to follow this instruction. Go to the tools, data grid, and press OK. And now you can see here a windows with the isosurface. So now I put 0.005 and in the ISO value and submit. I compare this orbital, but it's not so nice. So render the plus and minus the zoom value, and you can click submit. You can find the plot of the molecular orbital of this. If you change the value of the ISO value, change also the ISO value of the view plot. But I think 5 minutes. I click on submit. If you want to save this passage, so if I want to open another one with the same orientation and the same ISO value, you can save these states. You have to go to the file, save current states. We are in the maybe called my state. Okay, and save. Now close. And you can open another plot, another molecular orbital. I tried the file. If you put also the -- script, I think my state, maybe I'm wrong. No, it's okay. And you can find here the same orientation of the molecule, the same ISO value, and the rendering of the plus minus ISO value of this molecular orbit. And you can try what you want. In the end, if you want the fancy figure like if you want a fancy figure like this, you can also use, I think, this plot, this script is already done to plot each molecular orbitals and put it together. So if you run this plot, you can see increase and open and close and open and close for 60 times to generate all the images and put all together that I show you now. Okay, this is the images that you obtain in the end. All of the molecular orbitals plotted in the same figure. So I give you, I think, 10 minutes. Yeah. Okay. And then move to the graphene exercise. If you want to, and see. Okay, can we run if we set this thing off? Okay, I move on the exercise of the graphene because the time is not locked. So I want to finish almost in time. No, this is okay. Go back again to Barbara and move to example 2, graphene. This is also here you can find all the command that I used. Also you can find this slide in the repo directory. So this is the second system that we compute is a graphene surface, so it's a 2D periodic system. So to simulate the 2D system, we have to put a vacuum layer upper of in the 3D dimension, upper on the surface. So to avoid the interaction between the layer. So move on the example 2 graphene directory and go to see the PW input. Also here you can see a README file with all of the instructions that you have to follow to obtain the correct result. I don't know if I finish everything, but I will try. So see the PW. In this exercise, we will use PW to do free calculation. So the SCF calculation, that is the same that we used for the Z. The non-self-consistent calculation to compute the density of states, and the Benz calculation, that a type of non-self-consistent calculation. So first of all, the first step every time is to do the self-consistent calculation. So check the SCF calculation, the input for the graphene. So you can see here the calculation keyword. The default is the SCF, but now I put it to show you the difference. Now is the SCF calculation. This is the prefix, the same for the benzene. Now the out here, we will put now again the PMP. And also here the pseudo-dir that we have to put the same before. Okay, so we will copy the pseudo, but remember, I hope to remember correctly. Put here sample 0 for validation slash 1 so for it's fine. This is the system blocks with the information of the cell. Now, if you see IBRAV 4, before we use the IBRAV 6, now 4 for the graphene is trigonal Bravellati. Okay, go back to the input, the cutoff. In the electron, you can see the convergence threshold. So this is the convergence threshold to determine the convergence of the CF calculation, the position of the key, and the end, the key points. The grid of key points now is a periodic system, so you have to use the key points. Now we use here 9 key points along X, 9 along Y, and 1 in the Z, because it's a 2D materials, so we don't need more on the Z direction. Save. Okay, go to the, maybe I copy the path because I need then. So you can see here 3 different run script for the PW, dots and bands. Now we use PW. This is the same that we saw before, and also here you have to change the path of the primary. So put here build. If I write correctly the path, we will have the results. Yeah, still running, so you can see again the PMP directory. You can see in PMP the prefix dot extension 5. Okay, so you can see in the PW output, this is the same information that you see before, but now you have more key points. The CF calculation is the same, and in the end, you can see for each key point the bands, the value of the bands. Okay. Now, we want to compute the density of states of for the graphene. But before to run the DOS, we have to compute the non-set consistent calculation with the denser key point green. to have a correctly density of state. More density is better the density of state. So see the non-SCF input for the PW. Also here you have to remove the comment for out there and put the path for the pseudo here at the same. Now you can see here the calculation is non-set consistent. And also you can see here a denser grid of K points. Okay, now we have to modify the PW script. So modify the input file. So it's going no. So we call non-SCF and non-SCF. You have to modify also the output file because it's not rewritten the last one. Okay, and going to run the non-SCF calculation. Okay. I think already done. If you check the non-SCF calculation, you can see you haven't the self-consistent step. Okay, it's computed only one iteration to compute the energy in the code, and you can see the different K grid, the denser K grid. So this calculation read everything that you have computed with the PWCF and recompute the energy and all variables in one step. So now we have the non-consistent output with the denser K-point grid. So it's time to run the DOS calculation. So if you see the DOS input, it's very easy. Only the control blocks. So you have define the prefix and the out there and stop in the output of the DOS. So it's very easy. If you check, maybe I haven't the path. We copy the path for the script of the PP. Now it does not PP. Okay. Also, this is a serial calculation. It's very fast. So, and put here the path of your binary. Okay, I think it's already done. Yes. So you can see here, graphene DOS is the output, the density state. You can see all the Fermi energy, the energy electron, the density of state. But if you want to plot the density of state output. It's very easy because we show you only. It's okay. I have done. Oh. Okay, to plot this file, you can use what do you want. Now we have prepared a DOS script for the for GNU plot. You can see here the GNU plot script that read this file. So again, to visualize is better using the virtual machine and not the Barbara, the cluster, the HPC cluster. So we make an SCP to copy this DOS graphene slash is graphene DOS. Okay, here you can find now the DOS, the graphene.dos. If I using the script for the GNU plot that you can find here. Okay, generate the density of state plot. But you can see here, you can see the Fermi energy. So you can find the Fermi energy with the command grep Fermi on the NCF output. Here is the value in electron volt. Copy this one. Okay, copy and modify the DOS script here and put here the value and uncomment this line to set the correct Fermi energy. So now we try to run and you see the Fermi energy and the current density of state for graphene. So it's very late, but I want to show you how to compute the band structure of the graphene. So start with the PWSCF calculation that we have already done. So you have to perform not the non-SCF calculation, but the bands calculation. That is a type of non-set consistent calculation. So we go to see the PW bands input. You can see here the calculation bands. Also here put the out there and so on. I copy because I try to write as in path. What is the difference in band respective with the non-CF calculation? It's not only a denser K-grid, but you have a path of the K-grid direction, because usually in the band structure you see the asymmetry direction to see how to change the band. So for this K, we choose 4 points, the gamma points, the K points, the M points, and go back to the gamma. And for each step, you see here 20 steps, 10 and 70 steps. So now go to remodify the PW script now with bands, input and output. Okay, already done. You can see all of the K points with the direction that we choose. Okay, at this point, we run the bands calculation. If you check the bands input, is the same of the DOS input, so it's very simple. And also here you can run in serial for the bands, so I have to modify also here the paths on the binary. No, so the flash bin. Okay, and perform the band calculation. Okay, you can see here bands generate a lot of file. You can see with the plot of the bands for the graphene. This one you can see the number of bands, the number of key points, and so on. Also here we have a GNU script. This is the spaghetti script, spaghetti.gp script that read this file that bands already generate. So copy this file on the virtual machine. Again, here we have graphene bands.gnu and run the spaghetti script. No plot spaghetti, and show you here the band structure for the graphene and also the direction that we choose, gamma, K, and return to gamma. Also here you can find the Fermi level. So again, using the grep command to find the Fermi energy, copy the value, and put in the spaghetti script. Then we run, no. Yeah. Oh, no, I'm wrong. I changed the script on Barbara, not in a virtual machine. So I have to modify here. Okay. And rerun the script, and you can see here the Fermi level. First, to leave for the lunch break, I want to show you these tools to find the k-path to the direction, to the asymmetry direction. You can see. Okay. No. Ah, no. Sorry. I copy and put on the virtual machine. Okay. Maybe I. Oh, maybe Material Cloud doesn't work today. But okay, it's a tool that you use to find the correct k path to the asymmetry point for your system. I don't know why it doesn't loaded the page. Maybe Materials Cloud has some problem, but it's very easy. You upload your PW input and generate all the schema about the geometry, your asymmetry point path, but doesn't work. Maybe in the afternoon I will show you in yeah, but it's 30 seconds to show you. Okay, I have already done, I think. Yeah. If there are some questions you can write on attendee, so you can see everything about every answer to all of the question. And good luck for the exercise. Tell us maybe in the afternoon before start if you have success to compile and to run the exercise 1.
So now in the program, there should be a place for the lunch break. So if there are no more questions to be answered before lunch, then I suggest that we take the break, and based on the schedule, we should be back at 2 p.m. So good afternoon, everyone. I hope you had a nice lunch break, and I hope that especially our tutors are back from their lunch.
Okay, good afternoon, everybody. In the presentation, we try to explain you how to use Quantum Espresso to implement the calculation, to send the calculation that you had this morning in the lectures from Paolo Giannozzi, where you have the various possibilities that are implemented inside Quantum Espresso. And here I will try to very briefly to explain you how to use the input of Quantum Espresso to set up these types of different calculations. For doing this, you have to create an input that in Quantum Espresso is made like is a list of is a set of different name lists. I will show you afterwards some example of these name lists, like for example, okay, so like for example, this one, we have different name lists. We have a name list called control, one name list called system, one name list called electrons. Then if you do relaxation, you will see tomorrow, you will have also another name list called ions and one other name list called cell. But these are the essential ones for the simple SCF calculations. Then you have some cards, and these cards describe your system. For example, in this case, you have to list what are your atomic species. In this case, it's a chromium iodide system, so you have 2 atomic species, chromium and iodine. And for each one of these, you have you can specify an atomic mass that may be any. I mean, it's not complete. No, it's not always relevant, but it's always good to have the right number there. And then there is the name of the file of the zero potentials. As you have this morning, the zero potentials are the files that describe the interaction between the The ion, its core electrons, and with the valence electrons instead are what it's the computation is done inside Quantum Espresso. And then you have the description of the system in terms of coordinates. This is given by the atomic position card. It's like this. You have here, but you can also use other types of coordinates, like, for example, fractional coordinates. In Quantum Espresso parlance are called crystal, or also angstrom and others. And then there is, you have to specify how you want to sum inside the Brillouin zone. In this case, for example, you want to use an automatic to keep with mesh of Markov-Spack with 888 points and no shift. So coming back to the first page of my presentation, the most important of the name lists that you have to use is the system name list, where this is the list of the variables that are there, that can be set there, and that allow you to send a lot of different calculations, to set up a lot of different features of Quantum Espresso and running them. In this presentation, I will just limit to the most important cases. So I will show you how you have to set up calculations for a conductor versus a semiconductor. So a system with a gap and a system without a gap, or to say it better, if you want to integrate, if you want to use the Smilling for computing the Fermi level and the occupancies, or if you want to just assume that your system is an insulator and just use a simpler scheme for computing the occupancies. Then I will tell you how to select which kind of DFT you want to use, either the non-magnetic one with spin symmetric, so you just assume that the system has no magnetization, so that the occupancies of the spin, the majority and the minority channel of the spin are equal, and you use LDA or GGA. Then there are the magnetic systems, where instead you know that your system can be magnetized, but your magnetization is a scalar. So the energy of your system will not depend on the direction of the magnetization, but you just allow to have a majority channel and a minority channel, and you occupy them one independently from the other, and in this way to compute the total energy dependent of this scalar magnetization. And then instead you know that your system depends on the direction of the magnetization. Then you can also do calculations using spinors instead of simple wave functions. And in this case, the magnetization will become a vector, and so you can also take into account the direction of the magnetization. The third topic that I will cover will be the non-periodic systems inside the periodic boundary conditions. You have already heard about this morning briefly, and here I will just show you how to set up the calculations for these cases, and what are the main handles that you can use to avoid the artifacts of the fact that you're using periodic boundary conditions for a system that instead is an isolated, well, instead you want to simulate an isolated system. So just start from the occupation. As I was saying, occupations, the occupations are those that enter in any integration between the Brillouin zone, and that just tells you, and they confer a weight to each of the of Constant orbital that you are using in your calculation, in your the energy. And this function is in principle a step function. It's a step function that has a value of 1 for all the eigenvalues that have an energy that is below the Fermi level, and as a value 0 for those the eigenvalues that instead are above the Fermi level. The Fermi level is defined accordingly as the number, as the value that when you integrate all the occupations, you have the number of electrons that are inside your system. Obviously, this is definition in principle, but then in practice you can implement this step function in different ways. If you know, or if you already know that if you expect that the Fermi level is not it occurs in a place that is between an occupied band and this band, then in this case it's very easy to implement the step function, so all the bands that are you assume that all the bands are either fully occupied if they are below the Fermi level, or they are empty if they are above the Fermi level. So for each point, the only thing that you do is just to take the first NLEC eigenvalues and occupy them, and leave the other eigenvalues empty. And in this way, you are simulating an insulator, and it's okay, and it works very fine if your system is an insulator. But obviously, if there is no gap between the occupied and the unoccupied constant states, or if this gap is too small, what may happen is that your system will not converge. So you will not be able to use this and arrive to a solution. The other option is instead using smoothing. So in this case, the step function is replaced by a smoother function that must be summed inside the UN zone. In this case, in the input, you need to define the width of this smoothing. So your step function is smeared, so it's not a step anymore, but it's a function that has a width in which it decreases from 1 to 0, and this variable, and you have to do this with the Gauss variable that is defined in the system name list. The other thing that you can do is also to select several schemes for the smoothing. The default one is the Gauss one, that is robust and usually works straight away in all the cases, but is not very sophisticated. While instead, it's in most of the cases much better to use the Marzari-Vanderbilt scheme that instead is more efficient. So it allows with the same width to have a less variation, have a less influence on the total energy that you are computing, and this is the smoothing scheme that should be used for metals and for systems where you don't have a gap. There are also you can also select other types of occupations, like for example all the tetrahedral family of integrations. In this case, you integrate the step function as it is, so it's the function with the approved step, but you are using the integration that is a numerical integration in the UN zone. So what you need is, if you want to use this method, is you need to use a much denser number of key points, and you have also other difficulties because the forces are usually not variational, and it can be used. It should be used only for particular cases, and if you know what you're doing, and you know what you're doing, and you know that you need that type of integration. The other way to do this is you can also in principle specify the occupations in the input. In the input, you can put a tag where you specify what are the occupations of each level. This is usually used for if you're studying in an isolated atom, you have the generated levels, and you want to occupy only one of these, and leave the other empty to lift the rotational symmetry of your atom, in order that as soon as you occupy one, you leave the other one unoccupied, you are choosing an orientation for your atom. So in these cases, that wouldn't be treatable with a fixed scheme, but you don't want to have an equal occupation of the generated levels. You need to use the list from input variable, but also this is a very particular one and can be used only for particular cases, like for example isolated atoms. So I was saying that what you do when you use when you use this meaning is that you introduce a step function. This is and the step function just smears the value of your integrated function. So your function goes, instead of going from 0, instead of being integrated together with the steps, so having its integral value up to the Fermi level and then go to 0 abruptly, it just changes gradually its value from it just changes its value from the value that has the real function to the value to 0 in a range. This range is the Gauss value. And then the other thing that is important, as I was telling you about the fact that the Gauss meaning is less sophisticated but more robust. With the Gauss meaning, with the Gauss meaning, the derivative of this smeared wave, smeared step function is just a Gaussian. And in this case, you have that, but you can also use different types of derivatives of the step function. And according to this, and following this, you will have different sets of meanings. And they are, even if they are more complicated, they have the advantage that their influence, their change of the total energy is due to the fact that this value are that you just empty occupied value, that you empty occupy constant orbitals that should be occupied, and you occupy constant orbitals that should be empty is less has a lower impact on the total on the value of the wave function. So you can use a larger the Gauss, which means also that you can use a less dense number of key points, but at the same time having again the value of the total energy that is less influenced by the fact that you're using it as meaning. So the second, and this is all about the metals versus insulators. The second topic that I wanted to talk is about what kind of system you can simulate. As I was saying, you can simulate non-magnetic systems, and in this case, the only quantity that is of interest for you is the total density. The total density is just total density of electrons, and you are assuming that the density of electrons in the upper channel and the lower channel are the same, so you don't have any magnetization. And for doing this in Quantum Espresso, in the system name list, you have to specify the n spin equal, the variable n spin equal 1. You can also avoid to specify it because this is the default. So if you don't specify anything, the program will assume that you're working with a non-magnetic system and will occupy equally the two channels and work with a non-magnetic system. Instead, if you want to simulate a magnetic system, you have to specify n spin equal 2. In this case, you have you have two quantities. One is the total density. It is given by the sum of the density in the upper in the majority channel plus the density in the minority channel, and you have the magnetization. This is a quantity that characterizes your total energy. That is given by the difference between the majority channel and the minority channel. In this case, it's n spin equal 2. But as I was saying, you may also need to describe also the direction of the magnetization. For doing this, you have to specify the variable non-collinear equal to. With the variable non-collinear equal to, you will have that your system will be described by spinors. You will be able to define magnetization, the magnetization as a vector. So you have a direction for the magnetization. And the other thing that is possible in this case is also possible to add the possibility to use the Fourier relativistic formalism for the atoms around the Fourier relativistic orbit formalism, and add also the interaction with the spin orbit around atoms. It is only possible, obviously, when you have the spinors and you have a magnetization with the direction. Another thing that is very important about densities is that in quantum espresso you don't only have a cutoff for the wave for the plane wave basis set, but you also have a cutoff for the density. This is because it's true that the cutoff length is by construction 2 times the one of the wave function. So the cutoff energy is 4 times that of the wave function if you are using non-conservative zero potential, and because in this case your density is just the convolution of the wave functions so the product of the wave functions in each point. But if you are using ultrasoft or PAW, what happens is that you have also the augmentation charges, and so this is augmentation charges. So the density of the density of the FFT that you need to use is not only defined by the cutoff of the wave functions of the plane wave basis set, but it's also defined by the definition of these augmentation charges that are provided by the zero potentials. As for this reason, it's important when you are using PAW or ultrasoft also to specify a cut rho. This value is usually about around 500, 600 rebels are values for which these parts are well described. And it's important to remember this point. So just coming back to the magnetization, so we have that, as I was saying, the CF loop, the centrifugal loop starts from non-magnetic configuration, so you don't need to break any symmetry. Each constant state has a double occupations because you are occupying one for the majority, one for the minority state, so you adjust this expression for the density. And this can be done not only with the normal formula, so it's not only with n spin equal 1, but you can also do it with the non-collinear magnetism. In the non-collinear magnetism, if you just specify non-collinear equal true, but you don't initialize, you don't break the symmetry between the 2 directions of the magnetization, what happens is that you will be computing a non-magnetic system. And and in this case, what happens is that each constant or spinor will be doubly degenerate. So you can you will be able to find that each constant spinor may have 2 spin states that are different and may depend from the system. Okay, so the other case is the collinear magnetization. Instead, in this case, the constant states are distinct. You have 2 different polarizations, spin up and spin down, majority and minority spins, and the magnetization is in this case is a scalar, so it's not a vector, but it's a scalar, so it's just a number. This number is computed according to 2 different occupations. So you define one occupation for the majority bands and for the minority bands, and you just sum the 2 and to obtain the total charge, and you make the difference of the 2 to have the magnetization. In this case, if you want to start the calculation, magnetic calculation, you need to specify starting magnetization or to fix a total magnetization for the system, because otherwise, if you don't specify it, the program doesn't know how to break the symmetry between the 2, and it cannot break the symmetry by itself. There are 2 ways to break the symmetry. As I was saying, you specify either starting magnetization or fix a total magnetization. If you specify a starting magnetization, the system will start from a magnetic configuration, but it's free to do what it wants. It's free to converge to any magnetization that is specified. So you can specify a magnetization that is positive, but can converge to magnetization that is less than 0, or can also converge to magnetization that is vanishing. This is because you are just setting a starting point, but then the system goes towards the minimum of the energy that can be. And this is decided by the properties of the system. The other thing that you can do is to specify a total magnetization. In this case, the occupations for the majority of the minority spins are instead computed separately. And so this is done in order that you keep the specified total magnetization during the self-consistent loop always with the value of the total magnetization that you have selected. If you use instead the non-collinear magnetism, what you have is that you are using spin-offs. In this case, these are spin-offs. So for them is defined the operation of the spin operator. So you have a spin operator that is defined in the system, and your magnetization is defined as you applying bracketing the spin operator with the two values of the with each of the constant, which each constant spin and some and some of them. So again, just to show you how to specify the magnetization. So if we have, we can do that, as I was saying, with starting magnetization. In this case, we need to specify the starting magnetization for at least one of the atomic species. Like in this case, we have two atomic species, and we specify the starting magnetizations for the first one, and the new one where we expect to have a magnetic ion. And there are two ways to do that. I mean, previously, what happened in Quantum Espresso was that magnetization had to be specified in a normalized way. So it was the number that you had to put here was the ratio between the magnetization of the ion divided by the total valence of your ion. And this was a fractional number. And now it's also possible to specify the total magnetization of the atom. So what happens now is that if you specify a fractional number, the program will behave as before. So if you specify a fractional number, it will be interpreted as the ratio between the magnetization and the total valence of your system, as it was before. Instead, if you specify a number that is larger than 1, in this case, the system will not do like it used to do before, multiplying this big number 4 times the valence of the ion, but will take that value and consider that value as the magnetization that you have put in. So it's up to you to decide how to do that. And the other thing that you can do is to specify total magnetization that was saying, I mean, that as I was saying before, just fixes the total magnetization in each step of the first loop, and it is taken fixed setting a different Fermi level for the two channels, for the majority and the minority channels. What is the, I mean, if you, in case you don't know, what is the magnetic ordering of the system, and so you don't know what is the exact magnetization that you are expecting on the self-consistency loop, to have a better convergence, it's much better to never specify the magnetization for more than one species. I mean, you just specify the magnetization for one species, and then the system is enough to break the symmetry of the system, and the system will then be able to converge to the closer point of attraction, the closer minimum of the total energy, and so it will converge faster. The other thing that is important is not to specify a very large value of magnetization, because even in this case, the larger is the value that you put there, the larger is the time that the self-consistency loop will take to relax this value to the real value. And if the two are very significantly different, what happens is that it will take a lot of time and a lot of or step converging from one to the other. So I will just give values that are between 0.1 and 0.05. It depends on the balance of your system. The other thing that you have to remember is that when you use magnetization, when you compute a magnetic system, you cannot use the fixed occupancies unless it is fixed occupancies, because in this case the system must be able to use always fractional occupations. Otherwise, it won't be able to set them the magnetic system differently, because, for example, if your system is non-magnetic, what happens is that each level will be doubly degenerate, and the levels they will have to have a fractional occupation to at the real. So it is now possible to use fixed occupation if the total magnetization is specified with an integer value. In this case, the system will decide to occupy n plus total magnetization divided by 2 bands for the conjugate channel, and we decide to occupy n minus total magnetization divided by 2 bands for the minority channels. And the other thing that you can do is for atoms to specify directly the occupations with the input, the firm input occupation card. The other thing that you have to know about how to specify the magnetization is if you want to specify a definite magnetic. For example, in this case, we have an input of an antiferromagnetic iron oxide. In this case, we have that one iron has to have spin up, and the other one has to have a spin down. For doing this, as the two irons cannot be defined as the same species, you have to define 2 different species, one for spin up and one for spin down. And then in the starting magnetization magnetization variable, you have to specify starting magnetization equal to 0.1 for one of the irons, and for one of the iron species, and minus 0.1 for the other one. But this is a thing that you can do only if you already have an idea of what will be the occupations, or if you want to explore particular magnetic orderings in your atoms. Otherwise, it's a thing that just complicates the convergence of your SCF loop, and it takes time in the calculation. The other thing that you have to know about magnetization is that, as I was saying before, if you have a non-collinear magnetic system, you need your magnetization. You can specify not only the magnitude of this starting magnetization, like in this case, but you can also specify the direction where the magnetization is pointing. So you have 2 other more variables together with starting magnetization. You have angle 1, which is the theta, and the theta angle that defines your the direction, the azimuthal angle that defines the direction of the magnetization. And then you have an angle that you have let's see, this is the second angle that together with the other one defines the direction of the magnetization. With these 2 values and the starting magnetization, the direction is defined completely, and you can then define you can also orient each atom in a well precise direction. Okay, this comes to the third topic of the talk, that is the simulation of systems with reduced periodicity. In this case, the systems are, as you had this morning, were molecules, clusters, system with vanish, and other systems where where and other systems that have finite size and vanishing charge in the borders. And this system may be one-dimensional systems in case that you have you can simulate molecules and clusters, so systems that have 0 dimension. You can simulate one-dimensional systems that are systems that have periodicity in 1 dimension, like for example nanotubes and nanorods, but are isolated, but you assume that they are isolated in the other 2 dimensions. You can simulate 2-dimensional systems in the same way. You have periodicity in 2 dimensions, while there is a vacuum layer that separates the slabs one from the other. And then you can also have mixed systems, so systems that where you have periodic systems that embeds a defect, that embeds otherwise interfaces between surfaces, or such as, for example, superlattices, or otherwise molecules on surfaces. These are all cases of supercells, so systems which have a reduced periodicity that you want to simulate separating the system. These are a few examples that you will see this afternoon or the days afterwards. This is, for example, a molecule. In this case, what you have that that your molecule is defined with some coordinates, but then you need to define the size of your cell in order it is much larger than the size of your molecule. In this case, for the sake of making go fast the calculation, the cell is actually a little bit too small. So you have that there is not a there is not such a big mismatch between the dimension of the benzene and the dimension of the supercell, but usually you probably need to have a much larger value. The other thing that you have to notice here is that you can use the assume isolated specification that tells the program to truncate the interactions between the periodic images. This helps to have a faster convergence so that the system can converge faster, so that the spurious periodicity brings that the effect of the spurious periodicity is less relevant for your calculation. This is an example of a 2-dimensional system. Instead, this is boron nitride. Also, in this case, you see that you have to define a system that is periodic in 2 dimensions, and instead, in the other dimension, the dimension of the cell is much larger than typical. It's so large that the two slabs are not interacting one with the other. Also, in this case, you have an option for the assume isolated. You can specify assume isolated equal to D. In this case, what it does is just to truncate the electrostatic interaction between the different images, and this is particularly relevant when you work with phonons, because in this case, you have that the long-range electrostatic interaction are truncated in order that they don't show up when you compute, for example, the behavior, when you compute, for example, the behavior of the polar modes. So all this stuff means that all this, I mean, whenever you have to work with systems that are that a periodicity that is less than what the dimensional periodicity, so you are when you simulate them in a periodic boundary condition, you are adding an artificial periodicity. You also need, and the main factor that hinders the simulations and that limits the simulation and that can influence the simulations with artifacts is the electrostatics, because the electrostatic in periodic boundary condition is not completely cannot be completely eliminated by the calculation. So the things that one has to always take into account is that in practice, even if you are simulating a charged system, for the calculation, the net charge of the unit cell must be 0. Otherwise, obviously, the energy will diverge. So when you simulate a charged defect, there could be a compensating mechanism that cancels this charge that you have added, and this also brings other artifacts. All the potential that you are using are actually periodics, and so they cannot be just potentials that are defined within your cell, but they always are periodic. So the net value, for example, if you simulate an electric field, the net value of this electric field must be vanishing. The other point is that there cannot be a direct reference of the vacuum level. So the vacuum level is not unequally defined. It depends on the size and the shape of your cell. And it's possible to make it converge to a well-defined value that is the one for Daylight cells. You can make it converge to some value, but it usually depends on the size of your cell. And then the other point is that all the electrostatic moments between cells are generally ill-defined. So if you have a system that is not isolated, you cannot define the electrostatic moments of your cell. Dealing with periodic boundary conditions, you have to deal with different types of potential. There is the potential, the active potential. This is the electrostatic potential. This is generated by the electrostatic electronic density. This is a long range one. Then there is the exchange correlation potential. That instead is a short range potential. This also depends on the density, but it's proportional to the, it's somewhat proportional to the density, to the electronic density. So when the electronic density vanishes, the exchange correlation potential tends to vanish as well. And there is the local potential coming from the ion-electron interaction, and this is also at the long for the long range. This is also an electrostatic interaction. It's a Coulomb interaction, and so it's a long range. It's a long range part. The other thing that you have to take into account, and when we compute the electrostatic energy of a system of electrostatic ions, we need to perform an uneven sum. This is also a long range contribution that cannot be neglected. And let's now come to the R3 potential, and let's see how the R3 potential is computed in the default case. In the default case, the R3 potential is computed as a Fourier transform of the expression. As you can see here, we are neglecting the G equals 0 term. We are neglecting the G equals 0 term because this term is assumed to be cancelled exactly by a term that is neglected in the even sum that we considered before. So okay, the G equals 0 term should be 0 if the system is neutral. So n of 0 should be 0 if the system is 0. So in that case, you don't have to neglect it. But if n of 0 is not 0, so what happens if your system is charged because you have added one electron more than the neutrality level? What happens in this case is that this one should be 0, but we are neglecting it. So it's like what we are, and it's put to 0 because we are neglecting an equal term in the even sum. So what it means is this is equivalent to say that we are adding a constant background and plus that is equal to the charge that we have added to the total charge, and that the total charge of the system is 0 because we have added this constant background. And the other part that you have to consider is the long range part of the local potential that is defined by this value here. So the non-local, then this part here vanishes beyond the cutoff radius. So this is a local part. This is a short range part. Well, instead, the local part contains the long range Coulomb interaction, and this one doesn't vanish. So this one also contributes to the fact, for example, it contributes to the long range part. So it must be truncated if you want to simulate an isolated system. and it also contributes to the fact that your vacuum level is not always depends on the extension of the vacuum region. So as I was saying, the R3 the part that is neglected in the R3 part is compensated by the term that we neglect in the event sum for the charging system. In this case, the ionic electrostatic energy is computed as the energy of a point positive or some point positive charges that are immersed in a uniform negative background. And as I was saying, if the charges of the ions and the charges of the total charge of the electrons are not completely cancelled, we need to add this compensating background to cancel it. Another way to correct the behavior of the system is to use the Markov-Payne correction. In this case, if the system is neutral, so if it is not charged, we have that the total energy of the system converges as 1 to L to the minus 5, where L is the total size of the cell, is the separation between the periodic images. Well, instead, if the system is non-cubic, what happens is that there is also a dipole interaction, so the convergence of the energy goes only with 1 as 1 to the L to the minus 3. So it means that if you are simulating isolated system, it's always better to use cubic cells. For charged system, we have also taken into account the fact that the charges, so the charges in the charges that are localized in each of the periodic images interact one with the other. So also in this case, we have a term that we have two terms, one that decreases as 1 over L and one term that decreases as 1 over minus R to the 2. There is a third very important case that we need to consider when we simulate the periodic system, and is the fact that if the system is not centrosymmetric, what may happen is that the system develops a dipole, and developing a dipole develops an electric field between the two images that can influence the relaxation of the charge. Like in this case, we have a very small slab of nickel, and on top of this, we have a carbon oxide molecule, and a carbon monoxide molecule, and as we can see, the system is obviously non-symmetric, and there is a dipole that is developing here. And if you look at the calculation, what you see is that if you don't correct for this dipole, you have that in the middle of the system, you have a small electric field that that is due to the fact that you have a dipole. This electric field may influence the relaxation of your system and influence the geometry, for example, of your carbon monoxide molecule in your in this system. And we can correct this. We can correct this using the dipole correction, the adaptive dipole correction. And if we do this, we have that. We just add the sawtooth potential that cancels the electric field developed here, and so you have that. The potential is flat in the region, in the two regions of the vacuum region, and you have. And so you can your simulation is not affected by an artificial electric field. To do this, we need to start the so-called sawtooth potential. The sawtooth potential is started in Quantum Espresso using the TF field equal to flag that you have to set it to true, and this starts the sawtooth potential. If you want to model the sawtooth potential, you need to specify the direction in which this sawtooth potential is oriented. So, for example, the sawtooth potential must be used only for isolated system, and if you are using a surface, if your system is a surface, this direction must be the direction that is perpendicular to the slab, because obviously in the other region you have not the vacuum, and if you add the potential in that case, you are just breaking your system. The other parameters that you need to specify is the position of the maximum. So it's the position in this plot here, is the position of this point, of the peak, the maximum of the potential. And then the other thing that you have to specify is the region, the width of the region in which the potential decays from the maximum value to the minimum value. So the region where it passes from this value to this value. And so this is this width. You need to set this value in order that they are included, that they are contained in the vacuum region. So if they have to put in a region where there is no atom in the system. The other parameter that you have to specify to set up the potential is the output. So is this width. And okay, in the case that you want to use an adaptive Tooth potential, you have also to specify the deep field parameter and set it to true. This instructs the program that at each step it has to check the value, the difference in the potential between the two ends of your tooth potential, and increase or decrease the amplitude of the tooth potential in order that it exactly compensates this difference. This is an example of an input of a system where you are on the cobalt oxide of the nickel, on the carbon monoxide on top of the nickel surface, where you want, and we are here we are specifying, here we are saying the program to use the dipole correction, the self-adaptive tooth potential for correcting the dipole. So we are specifying both TE field and deep field, and specifying this through, then we have also here set the initial value of the amplitude to 0. So at the beginning, we don't compensate anything. So as the program detects that there is a difference in potential between the two, it just starts compensating. So it increases the amplitude of the potential until it compensates all the difference between the two, and then we get the exact value of the, and then we have a result like this, where we exactly compensate this slope with into levels. Here we have the intensity direction, here in the other direction, and so this is all I wanted to say to you, and thanks for the attention. And if you have any question for any other point, just ask. Thanks.
So thank you very much. So if there are no more questions, thank you very much for the talk, for the questions and the answers. And now it's time to take a break until 3:30 p.m. So you have 25 minutes to take a break, and then we'll see you back for the rest of the program today.
Thank you. Thank you very much. Thank you for the question. Thank you.
Hello again. Welcome back. So the coffee break is finished now, and we'll continue with our program. And I can see that Tone is the only one unmuted, so I suppose it's yours.
Yes, yes. So I may start?
Yes, please.
Okay, so let me start sharing the screen. Okay, so I suppose you can hear me and you can see my screen, right?
Yes.
Okay.
Yes.
Okay, fine. So my name is Anton Kokalj. I come from Jožef Stefan Institute, and I will be leading this hands-on session. So the main theme of this afternoon's hands-on session could be named convergence tests. And many of the items, many of the issues that Pietro explained in the preceding lecture, as well as Paolo in the morning, will be now, let's say, performed in practice. Now, as already introduced in the morning by Oscar, basically there will be 3 exercises. One will be about silicon, which is a semiconductor and has a band gap. And we will perform several convergence tests. So we will test for a basis set. We will calculate lattice parameter. We will test K points and so on and so forth. The second example is aluminum, which is a metal. And we will see how to deal with metal. So we will say occupation is equal smearing. This was the issue that was described in some length by Pietro in the preceding section. And then the last example of the day will be iron, which is metal again, but this time it is a magnetic metal. And so we will see how we can do collinear magnetic calculations. Now, before we go to the hands-on, there will be one operation which you will use in the following days, and that is to get the latest version of the exercises. And to this end, we have here this daily update script. And now I will demonstrate how this can be done. So basically now what you see is the virtual machine, and you have these day 1, day 2, day 3 folders. So if I double click day 1 in file browser, the day 1 opens, and then I can right click on the file browser, and some menu pops up, and now I will select Open Terminal, and you will see that I'm immediately located in the right folder, that is day 1 folder. And in this day 1 folder, there are several files and there are several directories. And one of the files is daily update. And now we can just do this daily update. So you write /daily update. And for those of you who are not familiar with the Linux or Unix operating systems, let me say that you have a kind of file name completion. So if you say // and you write just D, and then you press tabulator, the file name will complete. And okay, now I can execute this. Okay, and now the exercises were taken from the Git repository and were updated to the latest version. And if some of you obtained here some red lines, that is okay. Now, so what you will now find in this folder, in the day 1 folder, are several directories or subfolders, and we will use this example 2.1, example 2.2, example 2.3, example 0, example 1, and example 2 graphene was covered in the morning. Then you have here the lecture of Paolo Giannozzi that was given this morning. And then in each directory, so we can go even to a subfolder, for example, to example 1. So in each directory within this virtual machine, within this day 1, day 2, and day 3, you'll always find a README file. So if you double click the README file, you will get the description of what the exercises are about. These, of course, are very, let's say, a very short description of what to do, of how to follow the exercise. But then we have a more lengthy description. So in the morning, it was this file, example 012.pdf, and for the afternoon, it is this hands-on day 1 afternoon. And so here in this PDF, which I already opened it on the second desktop, you have a more detailed description of how to perform the exercises, and also some in some cases some physical description of what is going on. Now, before jumping to the first example, which will be silicon, let me introduce to you some preliminary item, and that is Quantum Espresso Emacs-modes. So Quantum Espresso Emacs-modes, and you have it there in your virtual machine. So Quantum Espresso Emacs-modes are Emacs-modes that makes the editing of Quantum Espresso input files a bit easier. So the first thing that you get is the syntax highlighting. So in this picture here, you can see this would be an input file for the pw.x program this input file consists of several blocks. This blue control system and electrons, these are name lists, and this purple atomic species, atomic positions, and K points, these are in Quantum Espresso jargon, they are called cards. And then, so if you do not mistype the variable, then the variables should be colored. But here is some mistake done on purpose. So if you mistype, then you see that the mistype variable is not highlighted, and this immediately you get kind of a hint, okay, I mistyped the variable. Now in the next page of these slides, there are some Quantum Espresso Emacs-modes commands, and now I will do a very short demo how this can be used. For example, if I don't know, let me just open some dummy input file. For example, I don't know, in TMP directory, I don't know, scf.in. I'm just imagining some name. Okay, the Emacs has opened, and now immediately here you can see, okay, this is Quantum Espresso pw.x mode. And now what I can do, I can press Alt-X, and then this MX appears here, and I can say, for example, pw space insert template, and I will get a template in the Emacs, a template in the Emacs with some description and so on. And this is one of the convenience of the Quantum Espresso Emacs-modes. So you get now a template, and you can start from such a template and then construct the input file. Another convenient feature is a kind of file name completion for the name list variables. For example, again, I can do Alt-X, pw space. So pay attention what is happening in this little window here. And suppose that I want to input the starting magnetization variable. So I start typing start, and then I press tabulator, and you see starting. And here I have all the possible choices. For example, starting magnetization, and then I can say, I don't know, some value 0.1. And of course, the starting magnetization, I need to specify for which species. Suppose that I would have only one species, which would be iron, I would do something like that. So these are these little features of Quantum Espresso Emacs-modes that helps you, let's say, editing the Quantum Espresso input files. Okay, this was just a very dummy demonstration. And if you go, for example, if you go now to the first example of this hands-on session, so we go to example 2. Here we have some input file of pw.x. If we double-click it, it will open in Emacs, and you will see that it is highlighted. And also here you have some comments. So in general, all the comments in the file are colored red. Okay, now let me go back to the slides. And yeah, so the first example, the silicon bulk. So you have to be in this day one example 2.1.silicon directory. And now I noticed there were some questions. What are these blocks, control system, electrons on the HEC-MD? And so let me try to describe that. Okay, this was already described to some extent by Pietro. So the control name list is about, in one sense, here we can say, for example, calculation. So we define what type of calculation. I can say SCF. SCF is default, therefore it was not written there. And so I specify what type of calculation with the control, and then also the files, like pseudo-dir and now-dir, and so on and so forth, which was already described in the morning by Oscar. Then the system name list is about a system, is about a structure. So what structure do I want to study? So the eBrav is the index for the Bravais lattice, and as explained in the morning by Oscar, suppose that I do not know what eBrav equal to means. I go here to the Firefox browser, and I have here this button, Quantum Espresso input description, and then I can click here this pw.x, and I find here this eBrav. And of course, for eBrav equal to, I will realize that it is a cubic FCC lattice. Why cubic FCC lattice? Because the silicon bulk basically has a diamond structure, and diamond structure is described with the FCC, with the face-centered cubic lattice, and there are 2 atoms per unit cell. There are 2 atoms per unit cell, and here we have some further description of the input. Now let me try to show you that indeed there are 2 atoms per unit cell for the diamond structure. So what I can do is, okay, now I have modified this file, it doesn't matter. I go to example 2.1 silicon, and now here I have this input file, and I can visualize the structure from this input file. So how I do that? To this end, I will use XCrisden. And so maybe one important warning for this afternoon session is that basically for every exercise we will do, because this will be convergency tests, we will plot the result. Plotting the result means visualization. And there is kind of a rule of thumb. When you visualize, when you use graphics, it is much better to use local machine, even if it is not powerful, than a super powerful supercomputer, because doing graphics remotely is super slow. And because we will use a lot of graphics, for this afternoon, we will mainly use virtual machine. If you are not using virtual machine, if you are using your Linux box, you can also use your Linux box, use your local machine, whatever it is. Now, to visualize the structure from the silicon, the input from the silicon structure from the pw.x input file. So what we do with XCrisden is we type XCrisden and then minus pwi. So what does it mean, pwi? It means pwx input file. And then I specify the name of the file. And now, okay, so here I have this, so here we see the input file that we loaded, so we can close this. And now here the XCrisden is asking me whether I want to reduce the structure. By the reduction means whether I want to reduce the periodic dimensions. But now I have a bulk system, a 3D periodic system. So I do not want to reduce. In another hand, if you would have a molecule, you could click here, reduce to 0 dimension, because molecule is a non-periodic system. If you would have a surface, which is a two-dimensional periodic system, then you can say reduce dimension to 2. But now I will say do not reduce dimensionality. Okay, and now this is what I get. If I want to get the atomic labels, I can go here to display, and I can click atomic symbols. Okay, and now there is a lot of atoms, and this is not very nice. It's difficult to understand where is which atom because no bonds are drawn. Now, in order to draw bonds, what we can do, we can go here to modify, and then to atomic radius. And what we will do, we will increase the chemical connectivity factor. So let's increase it by 10%. Let's write 1.15, because the bond is drawn if the sum of the covalent radius times the chemical connectivity factor is greater than the distance between the two atoms, then the bond is drawn. And so if I do that, now I really have these bonds, and now it is more easy to understand. But now you see I have a lot of atoms, yet here in the input only 2 atoms are specified, right? Only 2 atoms. So this NAT here means number of atoms, N-tip means number of type of atoms, and obviously we just have silicon. But we have here specified 2 atoms in the unit cell, and here there is a lot. So, but this is now nicely tessellated unit cell. If I just want to see translational asymmetric unit, so I can, you see here I have 2 buttons. It says nicely cut unit cell and translational asymmetric unit. And now, okay, I just see the translational asymmetric unit, but still, if I count, I have 8 atoms. Yet here in the input, I have 2 atoms. So what is going on? Well, what now I am visualizing is a conventional cell mode, which is kind of nice cubic shape. But there is a primitive cell mode, and this really has just 2 silicon atoms. And these are the 2 silicon atoms that are specified here in the unit cell. Okay, and so as a shortcut, you can press F3 and F4 button, and then you switch from one to the other. Okay, so with this, and now, okay, you can also see that basically this would really be an FCC lattice, because if I, let me do something like that, if I would just click these atoms here, you would recognize the FCC lattice, right? But of course, there are 2 atoms per unit cell, right? And so there are more atoms, but in principle, is the FCC lattice. Okay, now let me go back to slides. And so, yeah, so now you understand how this was input. And yeah, then the key points, right? Let us go to the key points. So here what we are requesting, so there are, as was explained previously, there are several ways how key points can be specified in Quantum Espresso. Either one is using automatic kind of a K-grid, where you specify like number of K points in one, the second and the third crystallographic direction, and then whether the mesh is shifted or not. And so this would be automatic, or you specify a list of key points, but then you need to do it manually, and this is much less convenient. For this reason, we are using here the automatic key point grid, and then the code constructs the key points for us. Now, if we want to run this input file, we can do. So this would be how it can be run from the virtual machine. This would be kind of a serial run. But before this can be done, we need to set the pseudo-dir. Pseudo-dir is a directory where the pseudo-potential files are located. But now let me on purpose do a mistake so that you will notice what happens if there is a mistake. So now here you see this pseudo-dir is commented. And so the code will not know where the pseudo-potential is. And if I try to run, and again, I will use this file name completion. So here I will just write PW, and now I will press a tabulator, and you see that immediately I have the file name completed. Now, if I run this, what I get, so this is now the standard output, is that the code complains that it cannot find the pseudo-potential. And this would be a default folder for the Quantum Espresso where the pseudo-potentials are located. But of course, I do not have this folder. And so it was a complaint. Now, we need this silicon Perdue-Zünger von Barth-Carr pseudo-potential. And this pseudo-potential in the virtual machine is located in this directory. So we can check this. And so those of you who are not familiar with the copy-paste in Linux, so you can basically select with mouse, and then you can press the middle mouse button. If you do not have the middle mouse button, then press both buttons at the same time. And so here, indeed, you see we have this pseudo potential. So if we uncomment this, and now you see it's highlighted, now the code will know where to take the pseudo potential. And if I repeat this, and now I would like to redirect standard output to a file. A typical convention for the input and output file names is that input file name ends with .in suffix and output files ends with .out suffix. So I will do something like that, and this will be super fast. And then we can look at the output file, and so we have this header, the Quantum Espresso papers, and then some information. So it is using just one processor because we didn't specify more reading input from which files, some information about the G vectors. And here is basically the information of the structure. So Brevet is index 2, the lattice parameter 10.2, this was this cell VM of 1, the number of atoms per unit cell, the number of type of atoms, and then the number of electrons. So that was 8, because each silicon has 4 electrons, and we have 2 silicon in the unit cell, so there are 8 electrons. And to describe 8 electrons, we need 4 Kohn-Sham states. Kinetic energy cutoff, and we just here, you see, we just specify kinetic energy cutoff for the wave function, but not for the density, and default is 4 times. This is what Pietro explained in the preceding lecture. Okay, then some crystallographic access, reciprocal access, and so on and so forth. Here we have the atomic positions reprinted, which key points were generated from this automatic key point grid. And then we have basically a self-consistent loop. So iteration one, and then the estimated accuracy and the total energy. And this then we do this self-consistent field, and how long it is proceeding, unless it is proceeding as long as we are reaching the specified convergence threshold. Now, and then when we converge, here we have then the key points, the key point and the eigenvalues for each key point. And then here we have the total energy and some contributions that were explained to total energy by Pietro in the preceding section. And then some timing input. Now, if you want to grep, usually one can take out automatically. We could write probably something like total energy. And we would, the grep would report, and we would see how the total energy is changing at the beginning, but then it is becoming very similar from one cycle to the next. Or we can say accuracy. And here we have estimated SFF accuracy, and you can see how it goes down from each next cycle, each next SCF cycle. It is better and better and better. Okay, so this was just a simple example of a silicon bulk, and now it is time to do. And here, okay, you have this graph description. Now it is time to do. Now it is time to do the first convergency test. The first convergency test is we will test which value of ECAT wave function, ECAT WFC, we need to use to have kind of a converged basis set. And so how this is done? So if you would do it manually, what you would need to do is to set a given value of ECAT wave function in the input file, let's say 16, and then run a calculation, and then take out the total energy. And then you increase the ECAT wave function, let's say to 20, and then you repeat the whole procedure, and then to 24, 28, 33. So doing this manually would be super, super cumbersome and a lot of work and very error prone. And for this reason, what is done usually is that one script this kind of a convergency test. And traditionally, traditionally Unix shell scripts have been used, but there are now more fancy alternatives which are cleaner, and these are PWTK scripts is one possibility, where PWTK stands for PWSCF, which is one of the main components of the Quantum Espresso, and TK stands for toolkit. Here you can click and you will be redirected to the PWTK homepage. And we can compare how does a traditional Unix shell script looks versus the PWTK script. So here is just a snapshot. If I go to our next page, so the two scripts, this is a shell script on the left, this is the PWTK script on the right. The two are analogous. And so how it is done, basically we do a loop over the ECAT wave function values. So let's say 12, 16, 20, 24, and so on and so forth. And then with the shell script here, we are inputting the whole input file. And you can see, okay, it's difficult to see because both colors are very bright. You can see that this ECAT wave function was set to the value of the ECAT variable. Then we perform the calculation and we grabs the kinetic energy and the total energy to a file, and then at the end we plot this. So this is how it is done with the shell script. This is okay, but I think that the PWTK script is much cleaner. So in PWTK script, what we do, we first load the input data from the, let's say, the input file that is there. Load from PWI means load from pw.x input file. And then we do the loop. This sec means sequence. This is like Unix sec command, which will return as a sequence of number. In this case, from 12 to 40 with a step of 4. And then this is a very nice feature of PWTK. We only need to set what needs to be modified. And here, what was modified in each loop was the ECAT of wave function parameter. And so we just say system, which is, well, this ECAT of wave function is a variable in the system name list, and we set this variable to the current value of a given loop. And then we run the calculation. So this line would be equivalent to this line here. And then we are taking out the total energy. This PWO means PWX output, right? And tot N for total energy. So we are storing this E tot value from this output file, and then we are writing it to the data file. So we are writing a line to a data file, the current value of the ECAT parameter and the E tot. So the value of the total energy for this particular ECAT of wave function. And then we are plotting the result. So the PWTK has this plot command. This would be X label, this would be Y label, and this would be Y format in C syntax, and we are plotting this. Okay, so just maybe a bit more about PWTK. So the basic philosophy is to keep the syntax very close to original input syntax. So here you can see the input file, the pw.x input file. And here you could see how this would be scripted in PWTK. It's very similar, so the names are the same. But here we have this ampersand and slash. Here we sandwich everything inside the curly braces. So to sandwich that inside curly braces is one way. The other way is that we can use double quotes. So when we have a variable like this $A that is expanded, so this $A will be expanded by the value of the A variable, then we need to use the double quotes. But the rest is very much very similar as in the PWX input file. Okay, now let us go. Here are a bit more description of PWTK scripting. This is you can, if you are interested, read later on. Here are some commands description what we will use. Here you have the web page and the documentation. And now let us do this first example. So you can either use this classic shell script or you can use the PWTK script. Okay, so I will choose, or let me open both of them with Emacs so that we will be able to appreciate one and the other. So here now you can see the PWTK script. So you see for every command that is there, you have a comment which describes what a given command is doing. And here would be the corresponding shell script. And you can see that this is much shorter than the traditional shell script. Okay, now let me go to this directory. Here I have this script. And now let me explain. Okay, I already explained it line by line, what it does. So basically loading the input file and then doing a loop over this ECAT wave function, different ECAT wave function values, performing the calculation for each ECAT values, and then writing the result to a data file and plotting the data file. Now, of course, if I was too fast and you got lost, you have here this README file, which explains what you have to do with this example. So it's super simple. You just need to run this script like pwtk ecat wave function .pwtk. Okay, and so you see that it is running. So for each ECAT value, the name of the file is different, and this would be the current ECAT value. And when everything is finished, and this is quite fast, when everything is finished, then we obtain such a plot. So here we have a total energy versus ECAT wave function. And let's say that the target precision is about millirad per atom. Here we have 2 atoms per unit cell. So let's say that the target precision is something around 2 millirad. And we can see that, okay, from one tick to the other is 5 millirad. So basically from one tick to the minor tick would be our target precision, which means that for this particular example, something from, let's say, this point on would be considered as converged. So we could use, I don't know, maybe 27 or 30 or something like that Rydbergs, and this would be considered as a converged basis set for silicon. Okay, with this, we have finished this example, and we can proceed to the next example. Now, the next example is the convergence with respect to key points. And now, so how we do, basically, we will go with the automatic K-grid, right? And so it's kind of key points automatic. And then we have 6 numbers here. So N key 1, N key 2, N key 3. This is, as I explained, the number of key points in the first, second, and the third crystallographic direction. And then this key 1, key 2, and key 3 is either 0 or 1. 0 for a non-shifted mesh and 1 for a shifted mesh. And now with the PWTK, this is super simple to do such a convergence test. So basically what we need to do is to load into PWTK the input data from the PWX input file that is there, and then do a loop over K, let's say 2, which would stands for 2 by, which stands for a 2 by 2 by 2 mesh. When the value will be 4, we will have 4 by 4 by 4 mesh, and so on and so forth. And so for each specific K-point grid, we are performing the PW.X calculation. Now let us go to this example 2, key points. And here we have this script. So this is how it looks. So we are loading this input file, which is now one directory back because we have it here, right? And then we do a loop. And for each specific K-point grid, we are doing the calculation. And then we are writing the results to ETOT versus key point data file. And at the end, we will plot the result. We will plot the result. So, and now let us run this script So PWTK, key points. And now you see that for each value of the K, the file name is different. So this, so that at the end, later on, we can investigate the input and the output and so on. And so these 4 calculations were performed, and then this, the result we have here. So this would be the total energy for 2 by 2 by 2 K point grid, total energy for 4 by 4 by 4, 6 by 6 by 6, and 8 by 8 by 8. And in the previous example, I said, okay, our target, let's say, precision in total energy is about 1 millirydberg per atom. And this means that for silicon, I would need to use 4 by 4 by 4 key mesh, because you see that from this point on, we have basically kind of the total energy does not really change very much, right? It is within, let's say, our target error bar. Okay, now, remember, right, that for the E cut-off wave function, it was about 30 Rydbergs, and then for the key point, it is 4 by 4 by 4. So this you have to memorize, because the next example that we will do, it will be example 3, will be about lattice parameter. And of course, if we want to calculate a reasonable lattice parameter for a silicon, we need a converged basis set, and we need a converged key point grid. And okay, so we can go to example 3, ALAT. And so what is this ALAT? This ALAT is kind of quantum espresso jargon for a lattice parameter. A lattice parameter. Now, if we go to our slides, you will have here the description, more detailed description of what you need to perform. But so we can also read a README file. And so the README file will say that read the alat.pwtk script and try to understand it, and then edit the file and set the requested variables. Because not all examples today are there that will run out of the box. So most of the examples you will need to change slightly to input something in the script. Okay, so I will open this alat.pwtk script, and maybe another, I will close a bit, I have too much open windows. Maybe another important thing that sometimes emerges is because you see in the morning you run calculations on Barbora. Now you are running calculations locally, and sometimes people are confused. So where, in which computer I am located? There is one super simple way to know on which computer you are located. If you are located on a virtual machine, then you have this colored prompt. See? And now you're using a virtual machine, so you have to have colored prompt. Now, instead, if I log to Barbora, you see that my prompt is black. So this is one way how to differ where I am. The other way is, of course, if you say hostname. Here, the hostname of the virtual machine is QE-emacs-2024. The hostname of the on Barbora is, of course, okay, login to Barbora, so on and so forth. So these are the two ways that you can differ. So for this afternoon, you have to use local machine. Okay, now I will open. So be in this day 1, example 2, 1 silicon, sub-example 3, ALAT directory. Let us open this script. And so here is the instruction: please uncomment and insert the value as determined in the E cut-off wave function exercise. And so I remember that 30 Rydbergs was okay. Please uncomment and insert values as determined in the key points exercise. And I remember that 4 by 4 by 4 shifted mesh was okay. And now what we will do, is we will do a loop over the R lattice parameter. And now is the question, so which value should I use for a lattice parameter? And maybe a good starting value for a lattice parameter is the experimental lattice parameter. So where I can get the experimental lattice parameter? Well, for silicon or for elemental metals or for elements, it is super simple. If you click here this icon, this is a periodic table of elements, and then I click silicon, and I read here somewhere should be lattice parameter, lattice structure, lattice constant, 4.43 angstroms. However, so this is experimental lattice parameter of silicon. However, in this cell DM, so if we go to the quantum espresso description, cell DM, it will say that it is the cell DM, these are crystallographic constants and so on. So the cell DM of 1 is specified in Bohr, right? So, okay, we know that 1 Bohr is roughly half an angstrom, but there, because we have X-Krisden, we also have this unit conv program, and I can say angst for angstroms, and then I go to this silicon and I input this value, and it will say it is 1026 Bohr. So 10.3 Bohr would be, let's say, lattice parameter. And so you see here what we do. We scan from 9.7, which is a bit to the left, to 10.7, which is a bit to the right of the experimental value, and with the step of 0.1. Okay, so I'm using this name for a name of the input files because I will use this for the name of the input and the name of the output. So I'm setting the lattice parameter, running the calculation, and here I am extracting the total energy. And then at the end, I will plot the lattice parameter, so the total energy versus lattice parameter. But I will do another calculation. So now I have this ETOT versus ALAT kind of data file. And so I have a series of data points. And suppose that I want to get the minimum. So where, in which ALAT there is a minimum, there is a quantum espresso program, which is called EV.x, which states energy of volume. Here, this program reads the input file, and then it will find the minimum, and it will print the minimum, and this is what is contained here. Later on, I will explain this. We will do this manually, but for the time being, we can just run this script. pwtk ALAT, and so it goes. You see 9.7, 9.8, 9.9, 10, 10.1, 10.2, 10.3. So it's quite fast. And this is what we obtain. And yeah, we can visually say, okay, the minimum will be around 10.2 Bohr, which is very close to the experimental value. And you remember from these morning lectures of Paolo Giannozzi, he said that LDA for, let's say, silicon, there was this table that LDA for silicon was doing quite a good job concerning the structure. So I can close this by pressing enter. And then this EV code was run with this input. And then you can see here in the value of minimum, the value of optimal lattice parameter in Bohr and in angstroms. And so you see that this our visual estimation was already quite good. Now, how this EV works, basically, this is kind of interactive program, and we can also look at this input file. And this input file is not very descriptive, right? So you have no idea what this is, but we can do something like that. We put ev.x, and ev.x will ask questions and we will provide the data. So it says lattice parameter or volume. In our data file, we have lattice parameter. We have lattice parameters, and here is asking which unit, atomic unit, which would be Bohr or angstroms. So I say atomic unit. This is why the first line here has this AU. Enter type of Bravais lattice, FCC, BCC, simple cubic, non-cubic. It is FCC for silicon. And now is the equation of state. And so we are using the Murnaghan equation of state, which is 4, which is why here was this 4. And then input file, basically this is the data file where these data points are written. These are this file. And then what would be the output file? Let's say that it is, this is the name of the output file. And then the code has find the minimum and has written this output file, which was here reprinted on the output. So here you see the optimal lattice parameter in Bohr and in angstroms. Okay, and now we can, for example, remember that this was the optimum lattice parameter. Okay, with this we finish this lattice parameter search, and we can go to the last example of the silicon, which is we will plot the spaghetti band structure. We will plot the spaghetti band structure. And yeah, so how it is done, this spaghetti band structure? Basically, we need a series of calculations. So first we need to perform SCF PW.x calculation, where we say calculation equal SCF. Then we need to perform a bands type PW.x calculation. So we say calculation is equal bands. And here we are specifying in this bands calculation, we are now not specifying a uniform k-point grid, but basically we are specifying a k-path in the Brillouin zone. Suppose that we choose from L to gamma to X to W to L path, and then we specify, okay, we want that many of key points along this k-path, and the quantum espresso will calculate that. And then with these bands.x, basically we are doing kind of a post-processing. These bands will transform these pw.x files to a format which is suitable, let's say, for GNU plot, with which we can plot the spaghetti band structure. And when the example will be fully performed, we will obtain such a band structure. Now let us try to do this. Let us try to do this. So we go to example 4, bands. And here you see we have this bands.pwtk script. So let me enter it. And so again, we need to, because suppose we want a good band structure, so we want to calculate the band structure with, let's say, the converged values of the parameters and with the optimized lattice parameter. So, okay, for the E-cutoff wave function, it was 30 Rydberg, and here I think it was 10.209, something like that. So, okay, I forgot. I can go looking at previous example. Yeah, so my memory was okay. So it's 10.209. And then for the key points. So at that point, you remember we used 4 by 4 by 4 and 1 by 1 by 1. However, when we are doing the band structure or the density of states, suppose that we are interested in the band gap, it is better to use a non-shifted key mesh. And here is a suggestion that we can use 6 by 6 by 6, 0, 0, 0. And there is a very good reason that I will explain later on why, when you do band structure plot and when you do density of states, if you are interested in the band gap, why you use non-shifted key mesh. So I will use this 0, 0, 0 here. Okay. And maybe a bit denser key mesh. Anyway, silicon is super fast example, so we can afford that. And then you see, we are doing the SCF calculation, as the name suggests. And then the second step is we are doing now the bands calculation. Now, the silicon is not a metal, and you remember in the first example we did, there was only 4 Kohn-Sham states. But suppose that here I want not just occupied, but also some unoccupied states. I can then specify number of bands equal 8, which means that we will be calculating 4 occupied bands and 4 unoccupied bands. And now here I have a key point specification in crystal units in kind of this underscore B means band. So this was done specifically for a band structure. And so here it says 6, and it goes like that. So there will be 6 key points specified. And then here we have this 26, which means that from the first point to the second key point, there will be 26 intermediate key points generated by the code automatically. And then from the second key point, special key point, to the third, we will have 30 intermediate key points, and so on and so forth. And then the last key point, we close with a 0. We are telling the code this is the last key point. Now let me try to visualize what key path this is. And so to this end, what I can do is excreasden, and now remember I have the input file, one directory back. So I can say minus minus pw input. Okay, and I'm not reducing the dimensionality because we have a 3D bulk system. Now I go to tools and I say keypad selection. And here I see the Bryson zone. And now I can display reciprocal lattice vectors. And so you see A star, B star, C star. And now let me go to the key points. So the first key point is 0 in crystal units, 0, 1/2, 0. That means 0 times A star, 1/2 times B star, 0 times C star. So this would be this point here. And you can indeed see, if you compare 0, 1/2, 0, we have 0, 1/2, 0. Then we have 0, 0, 0. This obviously is gamma. And you can also see excreasden is giving you the labels. So like it was written here, L, here we have L. Gamma, gamma. The next point is half, half, half. So half A star, half B star, and 0 times C star. This would probably be, I suppose it should be this point here, W. Yes, I know it's X. It is, so I didn't, no, wait a second. I didn't got it right. Is this one, yeah, X. So half, half, 0. Then we go to W, probably should be this one, yeah, and find 2, and then we go to K, which should be this one, I suppose, and this one. Yeah, so now you see that these coordinates here and here, they match, and here you have the labels, which also match with the labels in this command. And so this basically will be the key point that we will be calculating. Now you see that here is a lot of points, and here is a bit less points. Why? Because you see that these segments, the first 2 segments, are longer than the remaining segments. So this was, let's say, pre-calculated, so that more or less this distance between the key points is equidistant. Okay, so now we know what key path we will calculate, so I can close this, or I can just save this to show how you can get the information. So this is just total number of key points along the path, because this is generally is used for several programs, not just for Quantum Espresso. And maybe here I can say key path, and then I save. Now I have this file, and this is general. because some programs require such a input in terms of the integer fractions, and here would be in terms of the crystal coordinates, and this here you would recognize is very similar to this here. Okay, and now, so then we are performing this bands calculation, and finally we are performing, so this is bands pw.x calculation, then we are performing bands calculation, and at the end we are plotting it with a GNU plot. Okay, and so this is our band structure. But then if you read the README file, you will notice that the README file instructs us that we should grab the highest occupied level from the SCF output file and modify the GNU plot script. Okay, wait a second. So I can look at the output file, go down, and here you see highest occupied level is this number. Then I go to a GNU plot file, enter here the Fermi energy, basically the top of the valence band. I can also uncomment this, and now I can replot it. And now here you see, now I have the energy at the top of the valence band. And the reason why we are using non-shifted key mesh is that you see that these special key points, let's say at gamma, depending on the character of the band, we either have a band minima or a band maxima. But if we are using shifted K-mesh, then these special key points like gamma, X, and so on are not included in the K-mesh. And because they are not included in the K-mesh, we would miss the top of the valence band, and we would get a wrong, let's say we would get a Fermi energy which would not be precise enough. But here you see that at gamma point we have a kind of valence band maximum. And this is why we use non-shifted K-mesh in order to get, let's say, the correct Fermi energy. And now this is how it looks, this band structure. Okay, and now I realize I am running very much late. So I don't know, maybe we take some 5-minute break or so, break in a sense that you can, or maybe 10 minutes, so that you can try to run these calculations by yourself. But maybe 10 minutes is not enough. I don't know. Maybe I just go on, because anyway I will be too. I have how much time do you have? 1 hour more? Or half an hour more?
30 minutes, if I'm not wrong, right? 30 minutes.
30 minutes. So
okay, no, maybe we can go longer, but to ask whether to Karina or.
Yeah, but maybe I just proceed, and then you have all the instructions. So basically you have all the instructions written there, and then later on, because everything is happening on the virtual machine, later on you can do exercises, so you can repeat exercises by yourself. Otherwise, if we do now 10 minutes break, we will run severely short. Okay, so now we can go to example 2.2, which is aluminum. Now let me go to slides. Okay, and now with this aluminum, because it's a metal, there is this problem that for a given band, there are some key points which are occupied and some key points which are not occupied. And so we have basically this step function, which Pietro described in the previous lecture. And in order to treat this, let's say, integral over the Brillouin zone in some reasonable way, usually what one does is that softens this step function with some scheme that Pietro explained before. So this is one reason. The other reason is that sometimes when we have metal, the SAF convergence is not very nice, and then this kind of smearing helps with the SAF convergence. And so basically what we will do with the first example is that we will do kind of a three-dimensional convergency test. So basically we will test number of key points, so how dense the key point grid is, with respect to the type of the smearing, and let's say how much we broaden, right? These are three variables in quantum espresso. So this NK, you already met. So this is how dense the key point grid is, and then so the type of the smearing and how much we broaden. And basically with PWTK, here you see the snippet, we have kind of three loops. We have kind of three loops over the key points, over the type of smearing, and over the how much we broaden, and then we just modify the input that is needed, just modify the data that is needed, and for each value of these parameters, we perform a separate calculation. Now, this will take a while. Now, let us therefore submit it as quick as possible. So this is the example one of the aluminum, which is the Gauss. Here is the script. But because it will take a while, I will submit it immediately. So PWTK, the Gauss. And in the meantime, I will explain here what is going on. So, okay, this you know. So this is how we set the key points. Then a loop over different smearing scheme, Gaussian, Metfezi-Paxton, and Marzari-Vanderbilt, and different values of the Gauss. Then, okay, we set these parameters, perform the calculation, extract the total energy, and we are writing the total energy to a file. And then here, okay, this is maybe a bit more difficult. We are constructing, basically we are storing the name of the data files for later plotting, because here we have a three-dimensional scan, and we will do several plots. And with this, we are basically instructing PWTK how to plot. So we will do a special, a separate plot for Gaussian smearing, a separate plot for Metfezi-Paxton smearing, and a separate plot for Marzari-Vanderbilt smearing. And in the meantime, the calculation has finished. And here is the result. So you see this first plot and this multiplot at the end. This multiplot at the end was the instruction to do kind of a multiplot, and multiplot arranges several plots in a matrix-like layout. So here we have three plots. This is the result for the Gaussian smearing. This is the result for the Metfezi-Paxton and Marzari-Vanderbilt. This K4 means that this is for a K grid 4 by 4 by 4. K8 means 8 by 8 by 8. K12 means 12 by 12 by 12, and so on and so forth. And here we have the smearing. Here, and you can see that for aluminum, which is metal, 4 by 4 by 4 is not okay. Because you can see that when we go to a denser grid, we have a different result. So this would suggest that for aluminum, we should at least take, I don't know, 8 by 8 by 8 K grid, so which is denser than for silicon, because aluminum is a metal. And you can also see maybe when we do use larger smearing, then with a coarser K point grid, we can come closer to the energy of let's say, a denser K point grid. But you can see that with this increasing smearing, the total energy for the Gaussian smearing is very much affected. Whereas for this more sophisticated smearing schemes, at least for more denser K grids, it is much more flat with respect to the smearing. And even for these sophisticated smearing schemes, you can see that this K4, which means 4 by 4 by 4 K-point grid, it is not okay. It's not good enough. Although when we increase the smearing, you can see that we are approaching the value of the denser K-point grids. And so from here, what you can say is that suppose that we focus on Medvezel, Paxton, or Marzari-Vanderbilt smearing scheme, you could say, okay, K4, so 4 by 4 by 4 is not okay. Okay, 8 by 8 by 8 would be almost fine, but if we take 12 by 12 by 12, it is even better, because you can see that 12 by 12 by 12 and 16 by 16 by 16, they give more or less the same result. And then here we see that this is quite flat, and typically from this plot or from that plot, you can use a smearing of, let's say, I don't know, something in the range of 0.1 to, I don't know, 0.03 or 0.05. So something in this range of smearing would be fine. We should not go to 0, because then this effect of broadening this step function would be lost, and we can also end up with the convergency problems. So using either one or the other would be fine, and using, let's say, 12 by 12 by 12 K-point grid with a smearing around this region here, that would be fine. So this was a convergency test, with a three-dimensional convergency test, and how to quickly perform it with the PWTK. Now we can go to our next example, which is about charge density. So how the charge density is calculated. Let us open the script again by a series of steps. So first we do SEF calculation, and then we do a post-processing calculation, and at the end we plot that with X-Krisden. And again, also for this exercise, we need to input the parameters that we obtained in the previous example. I don't know, smearing, maybe Marzari-Vanderbilt, and the Gauss 0.01, 0.2, something in this range would be fine. And then the key points, 8 by 8 by 8 was already okay. 12 by 12 by 12 is even better. And I think aluminum is quite fast. We can afford 12 by 12 by 12. And then, okay, that's it. We can submit this calculation. So you see, it was super fast, and we get this density. So here you see, this was explained in the morning by Oscar. You have this instruction where you say minus script, and you load the X-Krisden script, and then X-Krisden immediately produce you a picture that was done in the previous example, and you save the script with this file save current state. And this, how you manipulate that, was already shown in the morning by Oscar, so I can skip that. And then I don't know who it was it Pietro or was it Paolo, who mentioned that, for example, with the PO pseudo-potentials, you can regenerate all electrons valence density as well as all total electron density. And this is then the next example. And so what are we doing here is we are loading the input file, and now we are changing the pseudo-potential. We are selecting the PO pseudo-potential, because then we will we will, and then for this all electron reconstruction, we need quite high cutoff for the density. Here is 500 Rydberg, maybe even this is not high enough, can be 1000 or more. And then all electron valence charge density has a plot number equal 17. So if you are just puzzled what this plot number 17 is, what we do, we go here to Quantum Espresso input description to PP. And here we should search for plot num. It's here. And here you have this code. 0 is electron pseudo charge density. 17 is all electron valence charge density, but it requires the pole pseudo potential. And then at the end, we are also doing it for plot number 21. And 21 is all electron charge density. And it requires, of course, pole pseudo potentials. Okay, I can submit that. So now it's doing the SCF, plotting the valence, all electron charge density and the total charge density. And then, of course, here it was not, no plot was produced, but here you have the instructions written how you can plot one or the other charge density. Let us just plot one of the two. Okay. Now, of course, I have here different plots, but maybe I go to a slides because there it will be nicer. So now you can see this is a kind of valence pseudo charge density, all electron valence charge density, and all electron total charge density. And here you can see almost no charge around the nucleus. And this was what was described in this morning by Paolo Giannozzi. So when we are using pseudo potentials, we have kind of pseudo wave functions which are smooth in order to get rid of these wiggles near the nuclei. When we reconstruct that with the pole, now you already see these wiggles here around the aluminum nuclei. But when we have all electron, then of course also the core electrons are reconstructed, and now we have a huge electron density around the nuclei as you would expect, of course. Okay, so with this, I was quite fast because I'm running out of time. We finished this second example, and now we can go to the third example, which is magnetic iron. So example 2.3 iron. Now, this example has two specifics. The first is that iron is magnetic. And the second is that iron is a 3D element, and 3D states are let's say hard states. And for this reason, we will be using ultra-soft pseudo-potential, because if we would use norm conserving pseudo-potential, the requested cutoff for the wave function would be quite high. But with the ultra-soft pseudo-potential, the cutoff can be lower. But then when we use ultra-soft pseudo-potential, then the default that E cut rho is 4 times the E cut of wave function is not anymore okay. And we will need to use a larger let's say factor than 4, something between Piero said before 6 to 10 or from 8 to 12, something like that. Okay. Okay, I will skip this. And in order, this was already explained by Pietro, how you plug in the magnetization. You say your collinear magnetization, you say n spin equal to 2, and then you assign a starting magnetization. So maybe we just do a quick look at the input file. Okay, so here you see this. Oops, I opened the antiferromagnetic bronch file. You see, you have two files. AFM stands for antiferromagnetic, and FM stands for ferromagnetic. So here we see, okay, first iron is a metal, we have this smearing, and then we have n spin equal 2 and the starting magnetization. We have just one atom, that is iron, and iron, everybody knows, is a BCC metal, and the code, the EBRAV code for BCC is EBRAV equal 3. So this is how ferromagnetic is done. On the other hand, if we want anti-ferromagnetic, which is here, what we need to do, this is what was explained by Pietro. So even though iron, we have just iron, but now we have one atom that is, let's say, spin up, another atom that is spin down, polarized. We need basically two labels for atoms. Let's say Fe iron 1 for let's say spin up, and iron 2 for spin down iron. And then we need kind of a supercell. So we need a larger cell because in this ferromagnetic, we have one atom per unit cell. And one atom per unit cell, well, you can just have one, let's say, spin polarization. So if you want to have anti-ferromagnetic, we need at least two. And so what we did, now instead, now let me show this. Let me show this graphically. Okay, so this is the B, you recognize the BCC lattice. And so this would be the translational asymmetric unit for the conventional cell, right? The primitive would be like that, but the conventional would be this one. And now what we can do for anti-ferromagnetic, or what here is done, we are pretending that iron is a primitive cubic. Primitive cubic, and then this is EBRAV equal 1, means primitive cubic, and then we say, okay, it's a primitive cubic, but it has two atoms. One is at 0, 0, 0. This is this one. And the other is at 1/2, 1/2, 1/2 in crystal coordinates. So you see, and these are these two atoms. So basically, this is how we do the anti-ferromagnetic setup. We are pretending we have a primitive cubic, and then we specify two atoms. Okay, but now for these exercises that we will do in the following, we will use the ferromagnetic because it has one atom per unit cell, and it is faster than using two atoms per unit cell for the anti-ferromagnetic. Okay. Okay, I will skip this. Then on the output, you can see that the code is reporting the total magnetization and absolute magnetization and so on and so forth, because we plug it in with this n spin equal to, we plug it in the magnetization. Here you have the explanation how this anti-ferromagnetic was done that I just explained. And now we do these convergence tests where I said that this default factor of 4 will not be okay. And so what we will do is a double loop. So the first is a dual, which is basically a factor. So we have this E cut rho, which is this dual times the E cut. And so the second loop is over this E cut wave function. So basically we will perform this kind of a double two-dimensional, kind of a two-dimensional scan. So let us look at the script. So it is located in example 1, ecut directory, and it is named ecut.pwtk. Okay, so you basically now you see in color what I just explained before. This double loop, we set the ecut wave function ecut rho, and then we perform the calculation for each values, and then we basically store the result, and at the end we plot the result. So let us submit this. And you can, okay, So you can see now it is doing. It will take a while because it needs to do quite some calculations. And while this is being calculated, because we are running out of time, I can go to a second example, and in the meantime, I can explain the second example. And the second example is how to plot density of states for iron, and it will be different than for a non-magnetic system, because now we would like with this density of states to plot both spin channels. And so there is a way how this is usually done is that, let's say, the spin up is plotted above the abscissa axis, and let's say spin down channel is plotted below the abscissa axis. And now let us look at this script, how this is done. So again, okay, we will wait. We will need to hear the input, the ECAT wave function and ECAT row values. Then we will perform the SAF calculation. Then we will perform for the density of states. In the meantime, I got the result. I will explain it later. We can to get let's say to calculate a denser to get more states. We can perform non-self-consistent field calculation where we use a denser key point grid. And in this particular example, we can use for the density of states the tetrahedra scheme for the occupations. And then we perform the dose calculation, and we will also perform kind of a projected wave function calculations, and this proiv wavefunction.x program do a projection. So basically it projects the wave function to atomic orbitals, and then we can have, let's say, kind of density of states projected to S states of iron, density of states projected to D states of iron, and so forth and so on. Okay, we will run this later on, but now let me explain this first example, which was about getting the proper values of ECAT wave function and ECAT rho. Now here you see this purple curve is for dual equal 4. So it is for a case where the ECAT rho was 4 times the ECAT wave function, which is default. And you can see that if we would use a dual of equal 4, so 4 times, then we would need to use quite high value of wave function, let's say 40 Rydbergs. From here on, let's say that we are converged. However, if we use a larger ECAT rho, then you can see that we can basically reduce the ECAT wave function. We can maybe use 25 for the if you use ECAT rho 8 times that of ECAT wave function. And now you can say, okay, what is the advantage? We can reduce one, but then we need to increase the other. Well, there is the advantage because there is a lot of operations on the wave functions and much less operations on the density. So we are basically speeding up if we use a lower ECAT wave function and a higher ECAT rho. So this is faster than the other way around. And so from this plot, we can say, okay, for iron, I can use ECAT wave function of 25 and dual of 8. So 8 times, so ECAT rho equal 8 times of ECAT wave function. And now I can input that here. 25. And this would be 8 times 25. In PWTK, we can, instead of calculating this, we can write this as a mathematical expression. This is no problem. Just take care that this is written together. because if you do something like that, this is not okay. There should be no white space. And okay, with this, we are okay, and we can run the script. So first the SCF calculation, the non-self-consistent field calculation, the DOS calculation, the projected wave function calculation, and this is what we obtain. Now this is a total DOS, like the title says. This is the total density of states, and then we have one spin channel. Let's call it minority spin channel, and majority spin channel, and the minority spin channel. Okay. Now this energy is quite some strange units are here. It is because we did not yet set the Fermi energy in the plotting file. But anyway, the Fermi energy probably will be somewhere here. And then you can really see, this will be the next example, that this purple spin channel is more occupied than the green spin channel. This is why it's called majority and the green is called minority. Okay, now this is total density of states. Now let us press enter. And now we get projections. So these projections were calculated with this PROIF wave function .x program. And now you see S states is purple. This is very flat. And for the spin up, and red for the spin down or for minority. And these states is this green and yellow. And this is known that for transition metal, so all the transition metals, if you consider them as a bulk, have, let's say, the S state roughly halfly occupied. And these S states, they are very broad. Let's say, I don't know, 10 to 20 electron volts. And they contain just, if we would go from, let's say, minus infinity to plus infinity, so we would have just 2 electrons. So we have 2 electrons distributed in, let's say, 20 eV energy window. This is why the density of states is very low. This is why you obtain such a tiny, let's say, density of states. On the other hand, the d states contain 10 atoms. So we occupy all the d states. And they are, let's say, contained within a few electron volts. So 10 atoms within a few electron volts means that we have a large density of states. And this is why we see this large density of states for d states and a low density of states for the S states. Okay, now let us plug in this plotting file the correct Fermi energy. So we can open this plot.gp, and here it says set Fermi energy to correct value. And I can go down, and then I will find, no, wrong file. I should use, no, it should be okay. Wait a second, it should be somewhere here. The Fermi energy is this one. So another way of not looking at the output file would be to grab Fermi, and immediately I obtain this. Now I can put this here, and I can replot. And now, in fact, you see where is the Fermi. The Fermi energy, it's here. And so now you can really recognize that we have more purple states occupied than the green states. Because if you would integrate this density of states up to the Fermi level, for the purple, you would obtain larger number of electrons than for the green. Okay, I press enter. And now here I also have this projected density of states. And I think that with this, the exercises for today are finished, and I just realized I am perfect. I'm perfect on time. Yeah, that's it. And so if somebody has some question, I can try to answer. So, and at that point, I will stop sharing.
Thank you all our tutors for today's lectures and also participants for attendance. The course will continue tomorrow. We will meet again at 9 a.m. on the same Zoom link. And I wish you a nice rest of the day and see you tomorrow.